All right. Thanks again. That was a really nice introduction. So yeah, true story about Eric getting me out of the mud. That was in 2013, I think. And I think it was during that stretch when we had the Moore tornado, the F5, and also followed by El Reno, somewhere in between. And I was down there in southwestern Oklahoma, and it wasn't a Hyundai Sonata. Who chases in a Hyundai? I did. Bad idea. Let me tell you, don't get a Hyundai Sonata. Not for chasing. I went off the road, and I had about 3 or 4, maybe 5 chasers who went straight past me and said, "Hi, Gabe." No one stopped to help, and I was really stuck. But you know what? Eric Fox was probably the 5th or 6th guy that passed me, and then he backed up and he said, "Need some help?" I said, "I sure do." And he quit his chase to help me out. And so he got me out of the mud, and Eric and I have been great friends ever since. So I really thank him for the opportunity to speak to you all. Again, my name is Gabe Garfield. I've been out of the storm chasing world for a few years now. Started a new life in East Tennessee with my wife out there, have a couple kids, and so some of you may not know me. In fact, I was talking to Tanner Charles. Do y'all know Tanner? Anybody know Tanner? He was saying, "Oh, it's going to be great to meet you." He was talking to me on Instagram, saying it would be great to meet you in real life. And he said, "The only trouble is that I don't know what you look like." I said, "That's a good point. My Twitter avatar is a tornado picture, actually, this tornado." And so I said, I'm the tallest guy in storm chasing, except for maybe Eric Fox. So anyway, it's a really great honor to be here, and we're going to talk about basic meteorology today. That's going to be the focus for this particular section. Then later on, we're going to talk about more advanced topics. So we're going to start slow, hopefully, talk mostly about how do we read weather charts, and then we're going to build on that in the second session. So let's get to it. So a little bit about my background, and I've talked a little bit about my relationship with Eric, but I come from Oklahoma, and in Oklahoma, obviously, we have some tornadoes, and I got very fascinated by them after my hometown, Stillwater, was hit by a tornado in 1990, and that really blossomed after the May 3rd, 1999 tornado. And I went to the University of Oklahoma for meteorology because that was the place to go. Ended up getting a couple degrees there, doing some work, particularly with the maximum wind speeds in tornadoes. That was my master's thesis. Learned some good things, and along the way, I had a number of other really great experiences. One of those experiences was Storm Chasers. How many of you have seen Storm Chasers? Okay, pretty much all of you have seen Storm Chasers. That was a good show. Well, if you've seen it, you might have seen me very briefly on there. I think everyone is entitled to 15 minutes of fame. I think I got 5 minutes out of that. It was a very, very bit piece. And basically how it went down was, Sean Casey, remember the tornado intercept vehicle? Well, he was talking to Josh Worman about, whether he should go into these tornadoes and, whether it was too strong and so forth. And they needed somebody to follow Sean not in a tank and film him going in, and so I was the guy that was selected for that, which I thought was an awesome job. It was pretty dangerous, but anyway, Josh was not really talking to Sean a lot, so Sean would ask him questions about, hey, how about this road and so forth, and Josh wouldn't necessarily answer really quickly, and so he'd be like, Sean would say, Josh, Gabe? And I was obsequious. I wanted to be helpful, so I said, okay, sure, I'll answer him. So I would tell him my thoughts about these things. And eventually what happened is that they ended up having too much audio of Gabe Garfield on this show, and they realized they had a problem because they couldn't edit me out. And so about halfway through it, they stuck a mic on me and introduced me as a character. So all that said, as I briefly appeared on a pretty awesome reality TV series, another thing that I did, let me back this up, was Vortex 2. Y'all might remember that. I was very privileged to be part of that experiment. That was something that, only comes around maybe every 15, 20 years, a field experiment of that magnitude. And so I rode in Mobile Mesnet 4 and also helped out with the forecasting for that. And then I spent, as Eric mentioned, about 7 years in the National Weather Service. I've worked in experiments related to improving tornado forecasts. So that's kind of a little bit about my background. We can get right to the meteorology now. All right. Let's see. Let's go next. I think it might be stuck. All right, there we go. So here are some of the tornadoes that I've seen, just to give you a background of what I've been able to observe. Some of my highlights: Dodge City, Kansas, 2016, probably my top chase of all time. You saw that on the first image there, and then also Moore, 2013. That was the loudest tornado I've ever heard. Just an unbelievably, really sad situation. And then you may have seen Hallam, Nebraska, before El Reno in 2013. That was the biggest tornado in American history. So I had the opportunity to observe that as well. Let's get to it. So in terms of what's ahead, this particular session I'm going to cover the forecasting approach and also really dig into the weather charts. So this is a map of tornadoes that have occurred in the United States since 1950 to 2019. I mean, you've seen something like this before, probably. This really shows where Tornado Alley is located. And the reason I wanted to show that is because most of those tornadoes come from supercell thunderstorms. So if you look at the numbers, it's actually like 70% of tornadoes come from supercells. If you're looking at the other 30%, that's like the non-mesocyclonic tornadoes. Basically, you have pre-existing vertical spin in the atmosphere that then is stretched by a thunderstorm updraft, and it forms a tornado. That accounts for about 30% of the tornadoes. The others are the supercells, and that's what we're really interested in because they're a little bit more predictable. So if you look at supercells and you talk about what they do, obviously, the reason that they're called supercells is because they are rotating thunderstorms. They can last longer than 7 hours. In fact, there was a supercell, I believe it was in 2012, during a high-risk outbreak that went from, I think it was northeast Oklahoma all the way up to Michigan and lasted 12 hours. Do y'all remember that? 12-hour-long supercells. And that, these thunderstorms can produce EF4, EF5 type tornadoes, as you well know. And they produce almost all the giant hail that you hear about that are greater than 4 inches in diameter. So we're really interested, and the point is, we're really interested in talking about supercells and how you can forecast these. Okay, for supercells, you need 4 ingredients. You need instability, moisture, vertical wind shear, and lift. And so we'll be talking about each of these categories in the next session, but for now, we want to really talk about weather charts and how to read them, so that will set the stage for learning about these various ingredients. So let's start with a surface map. Now, this is a surface map from May 24th, 2011. Do y'all remember what happened on May 24th, 2011? Anybody remember? It's one of the most violent outbreaks of tornadoes in recent memory. There were 3 EF4, EF5 type tornadoes in central Oklahoma, very, very dense, essentially collection of tornadoes there in central Oklahoma. I actually happened to witness a couple of them there in central Oklahoma. This is the surface map that was there on that day at about 3 p.m. And so you might look at this, and if you didn't know how to read a surface map, it might be very difficult to know what's important about this. And so the first thing that you need to understand about this is what these little station plots actually represent. And so for the next slide, you can see here that those individual plots are essentially sensors, weather sensors, located all across the plains there that have different readings. So obviously, the wind barb is probably one of the more common ones. That's showing the wind speed and direction. So in this case, you can see it pointing from upper left down to the lower right. It means the winds are coming from the northwest. You have temperature next to that. And as you're going counterclockwise around that, you have a weather symbol showing you what kind of weather is happening there. The dew point temperature, in the middle of that, the circle there, that's sky cover. It tells you whether it's sunny in this case, or partly cloudy, mostly cloudy, or overcast. And you have the sea level, pressure, and the pressure trend. Now, in terms of the wind barbs, these are usually measured in knots. So knots is pretty much like a mile per hour. I think you multiply a mile per hour, a knot by 1.15 to get what it is in miles per hour. So it's roughly the same thing, but slightly different. Top left, you see calm is that little circle with the dot in it. And the wind speeds go up all the way up to 145 knots. You can see that a single barb there equals 10 knots. You add a little half bar, that's 15 knots, and then you add another bar and so forth until you get to the flag. Once you get to the flag, that's 50 knots. It means pretty fast winds, and then it goes all the way up until you see 145 knots. Now, one of the things you can do with a surface map, if you're just kind of looking at this for the first time and you're not entirely sure of what you're looking at, is to plot lines of constant either temperature or dew point, and that can really illuminate, I guess, what's going on in terms of the weather situation. For example, you can see that the dew points here are in the lower 70s. These are the little green ones there. You can see Central Oklahoma has about a 70-degree dew point. That's juicy air. You might be interested in saying, okay, where is that 70-degree isodrosotherm? That's what we call it, basically a line of constant dew point. And so if you might put that in there and say, okay, that's where the moisture is coming in. And so when you draw that line, it's not exactly a science. There's a little art to it. People do it in different ways. But basically, you're trying to find out where all of the 70s are located. So to the west of that, you can see that line, you can see dew points in the 60s. To the east of that, you see dew points in the 70s. So you kind of put it a little bit in between. And that shows you where that really, really deep moisture is. All right. And the next thing you might want to do is locate the dry line. Now, the dry line is really important for severe thunderstorms and tornadoes, especially in the plains. Not so much if you go, say, Arkansas, Tennessee, Illinois. It's a little rare for the dry line to get out in that part of the world. But in western Oklahoma, it's pretty much a fact of daily life that the dry line is going to be somewhere nearby. And here it is. You can see it running from southwest Kansas down to southwestern Oklahoma. And you'll notice that the wind direction, and this is something that I would highlight here, is that the wind direction east of the dry line is south or south-southeast, and to the west of the dry line, it's from the southwest. And that's where the air is a lot drier. Typically, temperatures, you'll get into the 80s, sometimes even to the mid-90s. You'll see behind some of these dry lines. Warm front, you can see that here, and that, as the name implies, that's where the air is a little bit warmer on the southern side of that, and it's usually moving towards, or by definition, it's moving towards the north. It's the warm air is advancing. And you can see that from southwest Kansas, goes to southeast Kansas, and so forth to northern Arkansas. The cold front, the trailing cold front, is in Colorado, and then kind of arcs to southwest Kansas, and the low pressure center, the triple point, where the dry line, the warm front, and the cold front all come together, that's located in southwest Kansas. So it kind of, the point in the hand analysis is really, and you can do this on a computer. Obviously, I did it on a computer, but the name is meant to imply that you can look at these lines and see the weather patterns as they're coming together. So it's so much more observable now than it was before, right? Because you saw it before, it was pretty blank, really weren't sure what you were looking at, but once you put in some lines there, it really comes together and you start to see the weather patterns emerging. Something I see is, of course, the surging moisture. That's something that's pretty obvious. And also what I notice is kind of that arcing pattern that you see just southeast of that low center. That's something that, as a storm chaser, I would be looking at and saying, oh, there's probably some pretty enhanced convergence right there. So air's coming together. Maybe there's a chance of initiation of thunderstorms in that area. Okay, now we're going up. We started at the surface. Now we're interested in looking higher up in the atmosphere. So we're going to talk about the upper air map. So for this particular upper air map, this is also on the same day, the same event, May 24th, 2011. And you can see this nice, what you call trough of low pressure coming in basically where these solid black lines kind of dip down there. And you can see where I'm pointing out the constant height above ground. That particular line, if you follow it anywhere, will show essentially the height above ground that is 500 millibars. So this is the 500 millibar chart. It's done this way because reasons for the equations of motion. It's much easier to ingest this information than to do height, so they actually look at it a single level of pressure. And so it's not the pressure that varies, but the heights. And so that's what that's showing. And then you also have the constant temperatures. So those are the dotted red lines you see there. Typically speaking, the black lines and the dotted red lines are going to be kind of parallel. There's a reason for that we'll go into here in a minute. But sometimes they're not. And when they're not, that's usually when weather's happening. Typically implies what they call temperature advection. Advection means basically any quantity that is moved by the air. So you can move temperature, you can move dust, you can move anything by the wind. Anything that can be moved by the wind is technically advected by the wind. It's technically advection. And in this case, you're seeing some temperature advection there, which is associated with a really powerful system. All right, and then you also see the wind barbs, which we talked about before, which tells you really just how fast those winds are. You can locate jet streaks. Jet streaks are localized areas of higher wind speed in the upper part of the atmosphere, and they're associated with really important motions ahead of the trough that can really help you to understand where thunderstorms might fire. So what do you notice about the direction of the flow relative to the isoheights? It's flowing parallel. Do you see that? How the winds are kind of flowing along with the direction of these black lines. It's all in the same direction. And that's not an accident. And we'll get into the reason for that here in a second. So, but first, we want to talk about two essentially rules about pressure. So the first rule is that air flows from high to low pressure. So the reason for that is, think on a molecular level, right? If you've got a lot of pressure, that means that there's a lot of air that's kind of in the same area, kind of bouncing off of itself, and that means that the pressure in that area is pretty high. Whereas a low pressure would mean you have fewer molecules, it's a little lighter air. And so naturally speaking, that higher density air is going to move towards area of low pressure. So that's the first thing to know. And the second thing is that the wind speed is actually proportional to the magnitude of the pressure gradient. So what I mean here is that on the left you see this first case, you've got lower pressure on the left, higher pressure on the right, and then the same case, in the next case, you have the same pressure layout, but it's a lot closer. Those essentially isobars are closer together, those lines of constant pressure. And so in the first case, you see that the wind is relatively weak compared to case 2. And that's because the gradient, or the difference in pressure across those isobars, is a lot higher, so you get a lot stronger wind. So when you put this all together, you wonder, okay, now we're talking about upper levels of the atmosphere. You notice that the winds were flowing parallel to the isoheights, which are essentially like isobars. You think, why are the winds parallel there? Aren't they supposed to go, basically from high to low? Isn't that where you're supposed to go? Well, it turns out there's something else going on called the quasi-geostrophic balance. And that's a mouthful. And basically what that means is that the pressure gradient force is balanced by the Coriolis force. So the pressure gradient force is what we were talking about before with air moving from high to low. That's what that force is. And that's pointing off in the direction that you would think it would be. You're going, the air is flowing from high to low, right? You got the higher pressure down here, and it's going to low. But at the same time, you have Coriolis. Now, Coriolis is just essentially, it's not a real force, but it's an apparent force that happens due to the rotation of the Earth. And it's really hard to explain. It's a little bit high up to think about. But basically, if you're moving along with the wind, and your air is being drawn to the north by the low pressure to the north, and you say you're moving easterly, the Earth is curving underneath you to the right. And so what happens is that the air is wanting to go to the north, and then your Coriolis is pulling you effectively to the south. And this is only like an apparent force. So it's, I guess the best way to say it is like you've ever been on a merry-go-round, and you're in the merry-go-round, and you kind of feel basically pushed outward by the centrifugal force. That's not a real force, it's an apparent force. So it's something that you experience in a rotating reference frame. And because the Earth is a rotating reference frame, you do get that Coriolis force. And so what happens is that because you're basically in balance between these two forces, the higher levels of the atmosphere, you get a wind that flows parallel to those isoheights, or basically isobars. Again, this only applies above the friction layer. So you'll notice a lot different behaviors at the surface due to friction. Okay, some things to also keep in mind is that we do have some mandatory levels for where these pressure readings are taken from. It's at 850 millibars, 700 millibars, 500 millibars, and 300 millibars. Oh, and I should mention that, as you know, and as you probably know, the pressure decreases as you go up in height. So 850 millibars is closer to the ground than 300 millibars. So that's something to keep in mind. And this particular chart, what's nice about this is that all across the United States at the same time, National Weather Service offices release a weather balloon all at the same time. They do it 12Z, 12 UTC, and 0Z, which is, for, I guess, this time of year in Dallas, 12Z would be 6 a.m. and 6 p.m., right? And it changes, obviously, with daylight saving time. But the nice thing about doing this all at once is you get a nice vertical profile of temperature, dew point, wind speed, and direction, as well as pressure, all across the country at the same time. So you can build a nice weather model out of that. And that's really the advantage of doing it all at the same time. All right. Now we can talk about how to read a Skew-T log P. How many people know how to read a Skew-T log P? Okay, so the audience is pretty well informed, but we can start from the top here. So Skew-T log P, or as most people refer to it, it's just a Skew-T, is a way to analyze the vertical profile of temperature and humidity. These data are collected by weather balloons, as I mentioned, and include temperature, dew point, and wind. So the reason that it's called a Skew-T is because the temperatures are skewed in appearance. Log P is the log of pressure. And so what that means is that you're actually logarithmically decreasing as you go up in height. And so you'll notice that the pressures at the bottom are kind of closer together, say 900 millibars and 850 millibars are closer together at the bottom than, say, 300 and 250 millibars. So that's where the logarithm comes in. Okay, something to mention about Skew-Ts that's pretty important is that the Skew-T analysis assumes parcel theory. I won't get into all the details of this, but basically, you can think of a parcel as like a blob of air that originates really near the ground is the way we think about it, but it can really originate anywhere. But the key thing about it is that blob essentially stays intact, whether it's going up or going down. And that also, we assume that the rain falls out immediately, and that any parcel that's unsaturated, that means, basically the temperature is higher than the dew point, they cool at the dry adiabatic lapse rate, which we'll talk about soon. And what the lapse rate means is basically how the temperature changes with height. Dry air, it turns out, cools at a particular rate, whereas moist air actually cools at a different rate. And we'll go into the explanation of that. So these are the assumptions. In reality, dry air can mix in with moist air. So if you're thinking air that's originating near the surface, say that's feeding a thunderstorm updraft, as it's rising, sometimes dry air from around can mix in there with it and kind of reduce the amount of moisture in that particular blob of air. So parcel theory is not a reality. It's just a good approximation. And sometimes you do see that coming into play with the mixing and reducing, say, your convectively available potential energy. We'll talk about that here in a minute. Also, rain doesn't fall out immediately, so we're really not even considering the drag forces associated with rain. Okay, I just wanted to show this gigantic old Skew-T plot, not because we're going to go into this particular one in detail, but just to show you how high this goes. I believe this one goes to, let me go back up a little bit. I believe it goes all the way up to 50 millibars, and that's way above the troposphere, where all the weather is basically happening. The troposphere is where we live. In the stratosphere, we don't really give much regard for that, but it gives you an idea of how big that chart is. But we'll really be focusing in on this part of the thermodynamic diagram. So here is the Skew-T, log P, kind of zoomed in a little bit, and wanted to highlight the decreasing pressure, which means that you're increasing your height above the ground. Some of these charts are super nice. They'll not only have the pressure that's decreasing as you go up, the chart, but they'll also have the height, usually in kilometers, on the right side, so you know exactly how high above the ground that is. In this case, we just have the millibars, and you can see how the 900 and 950 are really close together, and then you go to the 400 and 450, and they're a little bit further apart. Again, log P, the logarithm coming in there. Isotherms. So these are the lines of constant temperature, and these kind of skew up into the right. And then you have the dry adiabats, which are actually exactly orthogonal, or at 90-degree angle to the dry adiabats. Now, the dry adiabatic lapse rate is about 10 Celsius per kilometer. That's how we think of it. It's a lapse rate, just meaning a simple rate at which temperature decreases as you go up in the atmosphere. And then you have the moist adiabats. In this case, it's a smaller number. That's when air is saturated. The other one was when it was dry. This is when the air is basically condensation has occurred. It decreases at a different rate than when the air is dry. It's about 6.5 Celsius per kilometer. And then you have the water vapor mixing ratio lines. And these will show you essentially how much water is in a particular volume compared to dry air. So the higher that water vapor mixing ratio, the more moisture you have in the air. So, if you're in Dallas and, May, you've got that air you can wear, you know what I'm talking about, where it's like really, really thick. You're going to be further to the right in terms of water vapor mixing ratio. Isotherms, you can see these all here. They go all the way from 30 Celsius all the way, probably minus 10 or 30. Yeah, minus 30, minus 40 C, so pretty far up. We usually don't think about that in terms of storm chasing. And then you have the dry adiabats, which are exactly orthogonal to the temperature there. Something I wanted to point out here is the difference between the dry adiabats and the moist adiabats, particularly as you go up. So at the bottom here, you'll notice that these are sloped a lot more to the left, these dry adiabats, and that means the temperature is decreasing a lot faster, no surprise, compared to the moist adiabats, which are kind of a little less sloped that way. But by the time you get up to the top of the troposphere, those lines actually come together a little bit, and there's a reason for that, and the reason has to do with latent heat release. So latent heat release, this is just basically talking about water in its different states, so water vapor, liquid water, and ice, and talking about whether heat is released to the environment or heat is taken from the environment. And so I want to focus on this part of this chart. So the water vapor, that's really the fuel for severe thunderstorms and tornadoes. So when water vapor turns into liquid water, that would be when, maybe you get a cloud, right? As air is rising up, it condenses. That's condensation. What is that associated with? Energy being released to the environment, right? So you're actually releasing heat to the surrounding environment. So that's why the moist adiabatic lapse rate is less than the dry adiabatic lapse rate. And that's because essentially when condensation occurs, it's releasing heat to the environment and it slows down the process of cooling as you go up in the atmosphere. Now, I will say I'm going to go back here. The reason that that slope gets a little bit more as you go this way is because by the time you get to the top of the troposphere, all that water vapor has already been condensed out. So you're no longer getting that warming effect way up there. It's only happening down here that it kind of mutes the cooling as you're going up in the profile there. Okay. So another way to think about this, in terms of parcel theory, is in terms of a hot air balloon. So obviously, you have warm, light air and cool, heavy air outside of that. Pressure gradient force in this case is going to be going up, and then gravity is going to be going down. So this is actually known in meteorology as hydrostatic balance. Basically, this is why you get basically lower pressure in Denver, at ground level than you do in Oklahoma. And in general, when your air is warmer than the air that surrounds it, when condensation's occurring, you get a net upward force, which is called buoyancy. And so we've already talked about how the moist adiabats align with the dry adiabats at the highest level, so we'll move on from this. Then you see the constant water vapor mixing ratio. This is really important too when you think about how these lines cross the temperature lines, and what that means is that say a 55 dew point in Colorado is not going to mean the same thing as it does. So 55 dew point here is not going to mean the same thing as it is in Colorado. So Colorado, because of the lower pressure up there, that's actually representing a higher water vapor mixing ratio, and so that's actually more potential for instability there. Okay, let's do an example profile. So we have temperature here. This is something that you might expect to see kind of in the springtime in the plains. You see the dew point temperature to the left of that. So let's say we want to find the lifting condensation level. So this is probably going to be review for some of you, but the lifting condensation level is basically the point at which that dry air goes from dry to moist. So that's when that latent heat release occurs, and that occurs, you can find that by taking the surface dew point temperature, finding that mixing ratio. We'll start from the temperature. So with the temperature, you lift it dry adiabatically, so following the surface temperature up the dry adiabat, and where that crosses with the mixing ratio associated with the surface dew point temperature, where that intersects, that's your lifting condensation level. So that's where that latent heat release occurs. And so visually, I would like to say that's associated usually with cloud base, roughly, more or less. Now, this is a little tough when you're talking about wall clouds, right, because there's pressure involved. It's rotating, so there's going to be a different condensation level there. But in general, the LCL is right where cloud base occurs. And then, now the next thing is, once condensation occurs, we're no longer going to be following the dry adiabatic lapse rate. So we're not going to be cooling like dry air does. Condensation has occurred, so it's going to be cooling along the moist adiabat. And that will help us define the level of free convection. So what that means is that even though condensation has occurred, there might be some negative energy that's kind of holding back the amount of explosive energy that you might find in the atmosphere. That's the capping inversion that you'd be talking about there. So you can follow that moist adiabat up to the temperature line, and where that intersects is the level of free convection. And once it gets there, every point above that, you'll see that if you follow here, that might be here where you see the clouds sort of bubbling above the LCL. There's a point where you kind of see, if you've ever been chasing, you see kind of like the stratiform type clouds, or the laminar clouds, not stratiform, at the base of the storm, and then above that it sort of bubbles. That area where it just starts to bubble, that's the level of free convection. And that's where air is, essentially that hot air balloon is warmer than its environment. And you can see that here. So there's that moist adiabat as it's going up, and that area in between it is the convective available potential energy. And so that just represents how much overall energy there is for updrafts in the thunderstorm. That's very helpful for a number of different things. And then I was talking about that capping inversion. That's the convective inhibition that's kind of in between there. That's the negative energy that you have to get past before you can tap into that cape. So until you can get past the convective inhibition, you're not going to realize that cape. So here's a thought experiment, is if you increase the temperature aloft, you can see that you're actually decreasing your cape. So if your temperature is not decreasing as sharply, then you're actually going to remove some of the instability in the atmosphere. But if you did it the other way, if you decrease the temperature aloft, then it would actually increase the cape. Now, what would happen if you increased the surface temperature? What would happen to the cape? It'd go up. So if you increase the surface temperature, basically you're moving this guy over here to the right. Everything shifts to the right, including the moist adiabat, and you'll see what happens. That area, the cape, gets a little bigger. You also decrease your convective inhibition, but you notice also you increase your lifting condensation level, right? So this is what happens during the late afternoon on the plains, right? As you're heating up near the dry line, you're removing that capping inversion, which is that little orange area in between, but you're also increasing your LCL. Well, not to get ahead of myself, but you know that the LCL, lower LCLs are usually tied into tornadoes, right? You need a lower cloud base for tornadoes. So it turns out that the first step in all of this is actually to get a storm in the first place. So increasing the surface temperature is good, right? So you can get a thunderstorm developing, requires some rotation, and then once that thunderstorm moves off the dry line, it moves into areas which have, say, lower cloud bases, which then can take advantage of that environment. If you increase the dew point, that's another way to increase your cape. So if you go from this to this, from this to this, you see how the cape really grows? It's actually pretty sensitive to dew point temperature. So that's something to note. If you see increasing dew points, you know, we're talking about that hand analysis, that can really show you where the potential for cape might be growing. And then the equilibrium level. So at some point, that moist adiabat, we talked about how the moist adiabat and the dry adiabat come together. And eventually, you're going to see temperatures in the stratosphere, they rise. So the moist adiabat will cross, or they call it the parcel temperature. It'll cross the temperature there, and that's where everything comes to equilibrium. And so visually speaking, that would be like the anvil level, right? So you've seen, you know, the anvil on a thunderstorm updraft, how it hits an invisible barrier and then kind of spreads out. That's at the equilibrium level. And sometimes severe thunderstorms are so powerful that they'll shoot straight up and bubble past the top of the equilibrium level. That's known as an overshooting top. All right. And for the final piece is how to read a hodograph. And this will be important for the second session. So hodograph is a chart that's used to analyze vertical wind shear. I've got a great image here of the Supercell, Oklahoma hodograph. This was from, I think, a bad wind profile, May 3rd, 1999. Remember May 3rd? That shows a very classic hodograph configuration there that was associated with violent tornadoes in central Oklahoma in 99. And this can be used, this particular chart can be used to quantify bulk shear, storm motion, storm relative wind, streamwise vorticity, and storm relative helicity. So that's a mouthful. Hopefully the next session we'll get into that in a little bit more detail and talk about that. But first of all, let's talk about constructing a hodograph. Now, a hodograph is constructed on a polar coordinate chart. So the radials are tied to wind direction, and the circles are tied to wind magnitude, like how strong the wind is. So let's take this case. So this is a wind profile that you might see in the plains during the springtime. So you have, say at the surface, you have southeast winds at 15 knots. Say 1 kilometer above the ground, they're 40 knots from the south-southwest. They kind of veer to, say, southwest at 45 knots at 3 kilometers, and then they really increase and veer out as you go up in the atmosphere. So how you construct the hodograph is you actually take these steps. First, you start with the surface wind, and you place that wind vector for that at the origin. So wind vector is just basically a way to represent the wind speed and direction. So in this case, we're interested in 15 knots. So we start at the center and point all the way until, basically to the northwest, until we get to roughly about 15 knots away from the center. And that's where we stop. And then we do the same thing for everything going up the wind profile. So now we move to 1 kilometer. You can see that's from the southwest at 40 knots. And we stop there, and then we go up to, I think I forgot this piece. So we actually do connect the vector tips. That's the key piece about the hodograph. So the hodograph is actually a measure of wind shear. So you're not actually looking at wind with a hodograph. It's actually a measure of the wind shear vector. So basically, the wind shear vector just means the difference between vectors at 2 levels. In this case, we're taking the difference between 1 kilometer and the surface, and all you have to do is basically the head-to-tail method, and you can see that you start at the surface and connect it to the 1 kilometer head there, and that's the 0 to 1 kilometer shear vector, and then you repeat for each level. So there's the 3 kilometer wind plotted. You can see the shear vector there. And then there's the 5 kilometer wind, and so forth. So then you can see how this shape emerges. And that is the blue line there, the blue lines as they connect together. That's the hodograph. And you can tell a lot about how a severe thunderstorm might be structured or organized based upon how that's configured. Okay. Again, notice that the blue trace is the difference of winds between the levels. It's not the winds themselves, it's the difference of winds between the level. It's the shear itself, the vertical wind shear. Okay, now for the final piece, we want to find the storm motion. Now this is something that was put together, I believe in the early 2000s by Matt Bunkers. He is an NWS gentleman, and he works with some other scientists to find this method to basically estimate how a storm would move, a right-moving storm would move, based upon the wind profile. And so for this particular method, what you want to do is find the average wind. Now, a computer is the best way to find this, but you kind of visualize the average wind here in this little red circle. That's where I would say roughly the average of all of those orange dotted vectors there. And then you would want to draw the 0.5 to 5.5 kilometer shear vector. So obviously one surface is right here, 1 kilometer is above that. So somewhere in between is where 0.5 would be, and then you'd want to go about halfway in between 5 and 6. And so that's what that green line is. Okay, now you would want to draw a line that is perpendicular to that runs through the average wind. It doesn't have to be perfectly, the average wind doesn't have to be exactly on that line. It just, the line that you draw through it has to be perpendicular to it. So you see there, where that crosses, you plot motion 15 knots to the left and to the right of that intersection. And so you see those L's and those R's. The L represents the left-moving storm motion, and the R represents the right-moving storm motion. So in this particular case, with this particular hodograph, we would expect that the right-moving storm would move, the supercell, would move to roughly the east-southeast at maybe 20 to 25 knots, give or take. And then the sort of mirror image storm, if it still existed, it would move off to the northeast. So this helps you to understand what you might expect in terms of storm motion. So, and I guess the last slide here, and before we move on to Jennifer's piece, is that high-resolution models are obviously very useful for determining where you might chase in a given day. And I'll admit that many times I've looked at them before I've done, hand analysis or looked at observations. But I will tell you that really observations are king, because there are many times where the models have been very, very off in their projections. So if you get a good handle on the meteorology and understand how to read these maps, it'll put you in much better position to intercept tornadoes. So with that, I guess I'll maybe have time for one question before we move on to Jennifer. Any questions before we move on? Okay, well, thank you.
We're happy to have you all here. Hope you enjoy your time here. So I work with the National Weather Service. I have been here in this office for 18 years, and I'm very familiar with the area. I am a former storm chaser. When my career started growing and then started having kids is when I kind of put it aside, but I used to chase with Tempest Tours was who I started with out of college. So I'm a graduate of Texas A&M University, and hey, yes, a couple here. All right, I see a lot of the OU here, but I am a graduate of Texas A&M University, started at the Corpus Christi office and worked my way up. So I am going to focus, I have a few slides before I turn it over to Dr. Karen, but I was asked to focus on reporting, how to make good reports, and what are important things to know about when you are reporting. And so this is very similar to what the National Weather Service will also talk about during our Skywarn storm spotting classes, but I have a couple of extra things that I want to add on for storm chasers who might be transiting across different areas too. One thing that I really want to highlight is reports matter a lot, and your reports matter. Spotters, storm chasers, general public even, they are the eyes and ears for the meteorologist out in the field, providing that ground truth reports that is assisting us in many different levels. A lot of times that ground truth is the missing link. If you think about it, meteorologists are going to be in the office, like you can see Dennis and I in this picture here, Dennis Kavanaugh, the WCM in the Little Rock area right now. Back when he used to work in our office, this is us working the radar on the evening of December 26, 2015, the day after Christmas tornadoes. And so we're in the office, we're analyzing the radar, we need to know what's going on out there. And so that's where the real-time, when you can safely do so, real-time ground truth reports really help us with making warning decisions as well. They're helping us to put the puzzle together of what the radar is telling us, or what we think it's telling us, and then what is actually happening out there. So when you're able to make those reports, it really assists us with deciding, do we need to continue a warning? Do we need to issue a warning? Is the hail actually smaller? We can drop the warning now or cancel it from there. So we're really relying on that real-time ground truth reports. The reports that are coming in also help us to tailor our message, not only for communities that are immediately downstream of those storms, but even a little bit farther out, maybe an hour or two. We can continue to provide information either internally with our partners. We're involved in public safety, emergency management, and also broadcast media. But we can also utilize our social media to try, people who are following us, to try and get that information and let them know, yes, you are in the path. We have it confirmed. You need to take shelter. Confirmation means so much more to people, we've learned from social science, than saying radar indicated. So having that confirmation when we can put that in really helps tailor the message and allows us, of course, to provide updated information when we're able to do so. This will also drive safety response actions from public safety officials. So we share the reports that you share either directly to our office with them as well. We don't include, names or exact, addresses and things like that, but we're saying, hey, in Roanoke, rotating wall cloud was reported. So they'll start to know what's happening and what might their emergency responses be, whether it's activating sirens, needing to go out and put up road gates, barriers, more posts on their social media to alert their local residences, things of that nature. Before I go forward on this, I'm going to step back on one. So I had a meeting with my counterparts recently also yesterday, and I told them I was doing this. And I asked them, what do you want me to tell this group? What do you want me to pass along? Because they don't chase in just our area. We know they're chasing all over the Southern Plains and farther than that. And they really wanted me to emphasize, too, that your reports, or any reports, are critical, especially in less populated areas. And there's a lot of times that I think, and it's nothing against anybody, but anytime if you are in an area that you can let us know that you're out there, or drop a link if you're running a live stream, we're not always constantly monitoring for that. So anything you can do to kind of help us edge us that you're out in that area and have something that we can maybe keep an eye on, we would greatly appreciate that, especially our West Texas offices. They really hit on that when I was talking with them. So these are a few of the must report. As a storm spotter, storm chaser, any of that, you can make any type of report to us, but these are the things, at least from a National Weather Service level, that we definitely want to know about. And that's going to be hail, penny-sized or larger. When it comes to damaging wind, I really push for people, don't try to estimate the wind speed. It's really difficult to do. Now, a lot of you here may have handheld anemometers, other wind-type measuring device. If you have measured winds at 50 miles per hour or greater, we really like to know about that. But for a lot of people, it's easier to focus on telling us what was damaged by the wind and making a good report that way. That's really helpful to us. And then we have pretty comprehensive wind charts. We use the tools on the Enhanced Fujita scale when we do damage surveys. So oftentimes we can take your damage description and equate a wind speed to us. So focus more on making a good report about what's damaged and describing it. Usually when people estimate winds, they overestimate when you're visually estimating winds. And if you want to, well, I don't really do that. Can you stand on a curb and watch the cars go by and tell me exactly how fast they're going? Usually we overestimate it. I can tell you I do it. I live on a main street, and everybody speeds down that street. So if you're estimating winds over 60 miles an hour, there should be damage. Now, I know out in West Texas and Plains and all, there's not always something to damage. So it's a little bit different for this group. But if you're in an area where some type of damage could have occurred, there should be something. That's why we issue severe thunderstorm warnings for 60 miles per hour, 58 miles per hour, and greater. With flash flooding, we just want to know about anything that is rapidly rising water, especially in areas that do not typically flood. For those of you who are mobile, you may not be familiar with is it an area that floods or not, but just we'll take any type of flooding information that we can get to help us make those decisions. And then the tornado one is pretty much hopefully clear cut. Any signs that a tornado might be developing with the rotating wall cloud, rotating funnel clouds or development of funnel clouds, and then actual confirmed tornadoes is something that we want to know about immediately. And we really do hope that you will take a few minutes to let us know that information, because it is critical to continuing the warning process and having a successful warning and getting the public alerted, getting them in shelter. So a couple of other things I just wanted to touch a little bit about. I'm not going to talk about the different types, but a couple of tips I wanted to touch on real quick was one with flooding. When you're making a report about flooding, in addition to answering, I'm going to have a set of questions here that you should think about when you're making a report. But in addition to that, when it comes to flooding, I want you to think about flood magnitude, flood frequency, and flood water behavior, and include that with your report. Flood magnitude is answering how high is high. Now, I am not telling you to go walking into the water to find out how high is high. Not safe. Please don't do that. But usually there's stuff around that we can use to gauge, whether it's an unfortunate car that's stuck in the water, maybe bushes, fences, something around that you might be able to estimate how deep the water is. Flood frequency is probably going to be a little bit more difficult for you unless you're reporting in an area like where you live. If it's maybe, let's say, a local chase, you know the typical trouble spots. You know if it's something that really doesn't happen a lot or hasn't happened before. So what you may also want to include is the floodwater behavior, meaning is it fast and swift moving or is it standing still? And usually the fast and swift moving water is the more dangerous with the power associated with it, and that's typically what we see in true flash flooding. And then it'll kind of settle down into the standing still while it takes a while to drain after that. So when it comes to measuring hail, we know that hail doesn't always fall in nice spheres, nice round ball-shaped different objects. Usually a lot of times they fall in spiky or oblong shapes. And then they also fall in multiple sizes as well. So kind of just a quick little quiz. We're going to start with the one on the left here. How would you measure this hailstone, the oblong hailstone? Would you measure it the average length, circumference, or see the longest length across it? Give y'all a second to kind of contemplate here, but the answer to this is you want to measure the longest length across. So it might be from spike to spike or from end to end. It might not necessarily go through the diameter of the middle of the hailstone there, but you do want to measure the longest length, and that's what you want to report. Now, as an Aggie, one of the worst days that I had working was when somebody called and told me they had a longhorn-shaped hailstone. I mean, how does that really happen? First of all, it was a storm that there's no way it had more than penny-sized hail in it. No way. Well, sure enough, this one little hailstone that could fell penny-shaped in the middle 2 spikes going out that measured 2.5 inches across. He measured it, took the picture, and sent it to us. And that's how it got written down, and that's the day that we had longhorn hail in our area. So a lot of interesting things happen. So when it comes to multiple sizes, we want to, I know it's fun to pick our favorite, but we want to make sure that we are measuring the largest size hailstone. You can go up and collect different sizes after the hail has stopped, when it is safe to do so, hopefully. And you can report it as penny 2 quarter-sized hail or penny 2 golf ball-sized hail, but make sure you are including what that largest size hailstone is. That's what we're required to document down, and we'll include your other notes in there as well. A couple of things to not do when you're reporting hail is we're really trying to still get away from marble-sized hail. Marble-sized hail used to equate to 0.5 inch or half-inch hail. As you can see, marbles come in different sizes. Sometimes we think people lost their marbles, but now what we equate 0.5 inch to is plain M&M. So it is a perfect excuse to have a bag of M&Ms with you at all times. Have a few for a snack so you don't lose your marbles, and then keep a few around to help measure if need be. And then one of the more common things that we're still really fighting against is pictures of just hail in hand. That's it, nothing else with it. That's probably one of the more difficult things for us to assess too, because a kid's hand versus a female hand versus a male hand is different. If you look at this picture, that hand is actually kind of cupped a little bit, and I will tell you, we have taken rulers out in our office and tried to recreate and measure to try and pick what it is. So if you're going to send us a picture of hail just in your hand, make sure there is some text with that about what that hail size is. It's better if you can just lay a more common object next to it and or have an actual measurement with it sent with that picture as well. But having some context with it, honestly, if there's an ongoing event, we're not going to have time to follow up probably in real time unless I've got somebody with a few extra minutes to either social media or message back at you or something like that. On the wind damage spectrum, just quickly wanted to give you an idea of what type of degree of damage we do see with different types of winds. Most thunderstorm winds a lot of times produce only about 30 to 50 mile per hour winds. But we do certainly have severe thunderstorms that will produce 60 to 70 mile per hour winds. So lightweight outdoor objects, including, yes, trampolines, they do fly at just 30 miles an hour, and not because of a tornado. So lightweight objects, especially ones that aren't secured, will start to break off tree branches, kind of smaller to mid-size as we get up 50 miles an hour. But as we go higher up on the scale, you can see kind of the jump from tree branches to actually shattering tree trunks, breaking them as we cross 70 miles an hour. And then on the far right there, the examples that we have, as you can see in the bottom, where we've started to take off a good portion of the roof there, including the roof decking. And then on the far side here, whoops, I turned that off. There we go, it's my fault. It wasn't my fault, it was a glitch in the back. No, there's actually an entire portion of the roof missing here. Now, both of these last pictures were from tornadic events, actually. It's been a very long time, thankfully, since in this area we've had basically greater than straight line 80 mile per hour winds. So we pulled a few from tornadic. The derecho events, they can keep those to the north. We're fine with that down here. We've got enough other stuff going on. So how to report to the National Weather Service. This is kind of an overview. If you want more about how to report to Fort Worth office, if you are here locally, we have our Skywarn webpage linked off of our main webpage there. But every Weather Service office ideally should have a public phone number at the bottom of their webpage. So utilize that to make your report. You can find us on Twitter, X, or formerly known as Twitter, whatever we're calling it now, and Facebook by just doing @NWS with the office name. This is a good way to send pictures and video too, along with making reports, but reports may not necessarily be seen in real time. If they're not seen in real time, we'll catch it at some point, maybe even the next day. We're really trying to, I think all offices see the value of sharing information on social media, but there's kind of a priority of things that take precedent, and if we don't have enough people either in at that time or in a transition zone, we might miss it in real time. So we're trying to get better about keeping a close eye on it, but calling our office, we have a lot of offices still have amateur radio teams that work with them, so knowing the local frequency of the amateur radio Skywarn groups, which may be county dependent. And then also at the bottom of every Weather Service webpage, there's an office email address. It's usually hidden under the please contact us, but you can also send reports, videos, pictures, even a day up to, or a week or so later if you want to, something to help us kind of fill in the gaps afterwards, we appreciate also. Some offices have Skywarn web pages too that might have other methods for how to report to their office. It might be a special phone number or some of them have online forms that homegrown ones that they've developed. So you might want to look for a local or nearby office web page. And then the MPing app is another one that we get information to. While we might have that system up and be looking at it in real time, some of us have alerts that come through our office when MPing reports are sent in, but they're delayed about 10 to 15 minutes by the time they go through the MPing server and then get into our office. But we do monitor that. Please know that the MPing app, which is free on iOS and Android devices, is not a weather service app, is instead part of a research effort that we're thankful enough to have access to visually see the data. It is great for reporting hail in particular, and different types of winter precip. I know we're still in winter here a little bit, but we will look at the MPing output to see where our transition lines are from freezing rain to sleet to snow. It's great for reporting hail, but the other descriptors are a little bit too limited. So with the MPing app, it's a series of preset drop-down menus. So for instance, like one of the flooding ones is like street and curb flooding may be approaching houses. Well, that's pretty vague, and you can't add any more information in there too. Hail is pretty straightforward, so it's good for doing that. But if you have a report of something else, I encourage you to use one of the other methods to provide more information to your local National Weather Service office. Tornadic activity is also easy to report on the MPing app, but I ask you that you please directly contact the local Weather Service office so they can make adjustments if needed to any ongoing warnings with that information. And it's okay to report directly to the office and through the MPing app as well. So I know a lot of people to use Spotter Network. It can kind of a little bit similar to MPing, but of course you can add more text in it. One thing I do want to say about Spotter Network is that we used to be able to ingest it in the Weather Service pretty quickly. That system went away last summer, and we do not see Spotter Network reports as easily and as quickly as we used to. I don't know, they're kind of in the works to bring that back, but unless we are actually logged into or pulled up and looking at the Spotter Network webpage, it is, there's a good chance that we may not see those during real time. So if you have something especially critical, please use one of the other methods to contact the Weather Service office and get that information to them. That's really the last slide that I have. Oh, nope, just kidding. I have one more slide maybe here. Real quickly, I'll make these slides available too, and these are on our Skywarn webpage too, so that Dr. Karen has enough time here. But when you're making a report, if you can answer these 5 questions when you're reporting to the Weather Service, it allows us to gather, process, and go with that report without having to take time to ask a lot of questions back. So we really appreciate that, especially using recognizable crossroads and streets is really important to helping us quickly identify what storm you're making your report from. And then the last thing that I have here is just real quick, if you don't know what happens when you make a report to the National Weather Service, we do document it that day. Again, we don't use information, we don't use your contact information. It'll be something as generic as golf ball size hail in Roanoke reported by a storm chaser, or golf ball size hail in Roanoke reported by a storm spotter, something like that. We'll send it out as a preliminary local storm report, or LSR, so that our public and our partners can see that and know what's coming at them also. And then it gets documented in our monthly storm summary. So we take all the damage and all the weather reports and we create a monthly storm summary. It goes out in storm event database, and your report then becomes part of a nationally archived database that is used for millions, maybe not millions, thousands of reasons, but by millions of businesses, construction companies, insurance, climatology research, things like that. You might be able even to go on the storm event database and pick out your report in particular there from an event. So that is all that I think, let me just check one more thing here on my notes from my partners, or from my colleagues. One thing, okay, I cannot say this as eloquently as Jason did, but Jason used to work in broadcast TV in the Panhandle for 13 years, and he wanted me to remind you all too that while we know that there's an effort, to get your footage, your videos on air, sometimes that comes at a cost. He's played that media game with trying to buy footage and things, please just remember that the Weather Service is not involved in that competition. We're not trying to compete with that. We really have a focus on public safety and trying to get your reports matching up with what we're doing for warnings and that. We will not reshare your videos or pictures, especially not without your permission, so you don't have to worry about getting out there free or without maybe any compensation, and we're using that information to make informed warning decisions.
Okay, so before dinner, I'm going to do a little light meteorology. We're going to just dig into a little bit of radar fundamentals. Probably we'll get through single pole stuff. I have a few dual pole things to show, and then I was going to talk about just advances in radar studies with tornadoes. So sort of a quick little three-part thing, but probably not really that quick. So Gabe had like a whole origin story, and I get like presentation panic, so I gave myself an origin story really quick so people know who I am. I basically started with the DOW program, the Doppler on Wheels program, in 2004. Actually, I was out with Gabe in a hurricane. He just reminded me of that today. I forgot about that, where we almost fell into a cliff. I chased some crappy nothing storm. I was into tornado research, but so when I went out for the actual project, it was sort of the end of tornado season, so all I ended up doing was basically ferrying a vehicle back to the headquarters. It was really exciting. Like I said, hurricanes really ended up being my first mission. I still hate them, but I still do them. This is how a hurricane mission was sold to me. I was not a meteorology student. I had come from physics, and I thought it was going to be a beach and hanging out with friends. And even when I was asked, what to pack, I was supposed to pack like pillows and sleeping bags. And anybody who's chased hurricanes obviously know that that's like the exact opposite of what a hurricane mission is. And this is for Gabe too, but he's probably not here anymore. He was in the rental vehicle, but we were on this cliff with this slumping leg during Hurricane Francis. And I vowed never to do hurricanes for a very long time, and also never to deploy on bridges, barrier islands, or beaches. But I think I've sort of broken that rule. 2005 is actually when I saw my first tornado out in a field project. I was so proud of that picture. It was amazing. I was in a radar. It was the rapid scan radar, and it had no radar display, so it was really not that exciting, except for looking out at the tornado. And both myself and the people in the radar, I think this was sort of our first tornado. We're like, oh my God. We forgot to put up the legs on the radar truck, and we zoomed off, dragging the legs. 2006 then was Storm Chaser was the boring year, the year that never happened. So lots of publicity shots and filming, and nothing ever made it to the field. It was actually, I would say, the year of sunrises and sunsets. So after I was doing all that, I got recruited to go to Germany and France with the Dow. And this was before GPSs were really good. So I was driving the Dow all around Germany and France. And they gave me a GPS location of where I was supposed to deploy the Dow and take data. It was in the middle of a farmer's field, and I thought, sure, and I just drove right out into the field. Didn't even think twice about it. The German farmer that came out was very angry, but he did get us out of there. Then I saw where the real deployment spot was, and the German farmer, he was actually very nice. He came and he brought over cucumbers and bread and wine. So after ruining his field, he was very hospitable. So now, I've sort of been doing some of this for 20 years. I've been with the Dows for 20 years. The Dows have grown, my roles with the Dows have grown, but this is sort of where I've ended up there. So I had to give an origin story. Okay, so radar, what I'm really here for. I have to say, I was looking for really good graphics. I was going to make my own graphics, and those were horrible, but the internet doesn't have the best either. So very basic, when we think of Doppler radar, we think of some sort of dish focusing some sort of pulses of energy. It hits objects, raindrops, hail, whatever, and part of that energy scatters out into space and never comes back. And then some of that energy actually comes back to the radar. So your basic your basic single pole radar is, again, sort of a bad graphic, something like this. Again, you hit this energy, you get some back. And very simply, in some ways, it's very simple. You transmit, you make some pulse of energy, some high energy pulse. It goes out, like I said, hits this, and you do it frequently, and we call that the PRT or the PRF. So you're doing that very fast, and you do it for a certain amount of time, and we call that the pulse length. And then the antenna focuses that energy out into where you're looking. Then you switch between your transmitter, because you don't want to have your transmitter and your receiver on the same line, because you'd blow out your receiver. Then you switch and you receive, and you get back that signal. So you transmit, and then you switch into receiving, and then you take all those pieces of energy, all that information that goes with these pieces of energy, and you make pretty pictures, preferably in the form of carbon-42, and not what radar scope uses. But you make very nice images in the data that you can see, so data that you see in your radar apps. Your basic products that you get 3 basic products from single pole radar. You get power, which, as people know, gets turned into reflectivity, but power really is just the power coming back to the radar. And then you get these 2. You get something called Doppler velocity, and with that you get something called spectrum width. Looking at this horrible diagram, I don't think I was very happy with it. This sort of says, this shows in picture what I said. So the idea, again, is you transmit. This is your duplexer or circulator. That's what switches back and forth between transmit and receive. You send out your pulse of energy, and then you get your energy back, and it goes down the receive channel. But the one thing that you do keep track of also is you keep track of your transmit pulse, because you need to compare what you're doing with that transmit pulse to the pulse that you get back. So you need to know the properties of that in order to calculate things like your Doppler velocity. All right. Like I said, the internet was not good for me. But again, these are your 3 moments that you get back. Reflectivity or power, that's the first moment. The second moment is your velocity. And then the third one is, like I said, the spectrum width. And this is down here, this is your noise floor. So there's some level that you can't measure below, called the noise floor. And that differs for different radars. It's a function of your radar, it's a function of your signal processing. A lot of things come into that play. But reflectivity then, it's your area under this curve, what you get back. Your velocity, that would be your peak, your meters per second or your knots. And then spectrum width would be your variance, so how spread out your Doppler velocity estimate is. So if it's really tight, that means that your Doppler velocity estimate isn't very spread out, and there's not much variance in it. But if there's a lot of variance, that usually means that there's a lot of turbulence in your field. Sorry, I'm trying to talk fast so everyone gets to lunch, catching my breath there. So just other sort of terminology stuff, and I'm probably touching on terminology that people, if there's stuff you are like, why do they use this word? Ask me. I was just trying to go through some of the things that people use a lot. Range, obviously how far you look out with your radar. There is a theoretical maximum based on your radar properties, how far out you can actually look. And then elevation, so your beam elevation, and that's just what elevation level or what height you're scanning at. And just reminding everybody, as you go farther and farther out, you're getting farther and farther from the ground. And this nice graphic didn't have that, so I curved it. The other thing that also happens is your Earth is curving. So you're getting farther from the ground, and your Earth is curving. In terms of your beam, so going back a little bit more to your beam here, again, I'm trying to put out some terms that maybe people hear and aren't 100% sure what they mean. So the first thing is your range gate or your gate. When you're sampling, you hear people talk about gates or pixels or something. And that's just how long your gate is or your pulse length is. So like I said, you send out a pulse, but you send it out for a certain amount of time, and that's something called your pulse length. And a lot of times people match this with their gate length, so what they receive back. You can oversample, but not everybody does that. And that just determines your resolution along your radial. The other thing, which I want to remind people of, is these are pulse volumes. These aren't actually two-dimensional. They're volumes, so they're 3D. So not only are you looking that way, you're also looking up and down and left and right. And the farther you get out, the farther your beam spreads. So the farther you get from the radar, the bigger your beam is, the worse your resolution is. So you're farther from the radar, you're high up above the ground, and you have bad beam resolution. Your gate length doesn't change, so that's nice, but then you're really mismatched because you have this ginormous beam, and you're very high up, and then you have this tiny range gate, which a lot of times is pretty silly because you're not actually resolving what you need to resolve. Beam width. So when people talk about beam width, they're talking about the half power point, or sometimes you hear people call it the 3 dB beam. So that's when it's down 50% from the transmit power. So your antenna is this nice thing that's focusing energy out. You have this beam, this is your beam width. And on the side of your beam, there's still energy that's out there. It's not just this little focused 1 degree beam that you have. You still have other stuff on the side, and I'll talk more about that. But what's really doing a lot of the work is your beam width, what falls into that 50% or that 3 dB beam. Just as a quick note, the 88Ds, they're 1 degree beam radars. DAOs are 1 degree beam radars. They oversample, so you see nowadays, we see something like super resolution. That doesn't mean that their beam width is actually, their physical beam width has not changed, they're just sampling it more often. So just FYI, it doesn't make it worse data, but you didn't change your physical beam width, you just changed your sampling. All right, PRFs or PRTs. And this is what you really care about if you're trying to do velocity measurements. So pulse repetition frequency. Frequency is something measured 1/seconds. Sometimes people use pulse repetition time, and that's in seconds, which is just the inverse of your frequency. So it depends who you're talking to. People use it in different ways. But yeah, just as a reminder, they're just inversely proportional to each other. So again, just showing you what this looks like as you're transmitting. You have some pulse duration. That's what I was talking about, your pulse length. So you're transmitting for some amount of time. You stop listening for a second, and then you listen again, and you get it back. Between these pulses, that's your PRT or your PRF. So how often you're pulsing. So if your PRT, your pulse repetition time, is high, large, that means you're not pulsing a lot. That means, if your PRT is 10 seconds, that means you're pulsing every 10 seconds. If your PRT is 1 second, you're pulsing a lot more frequently. And again, inverse with PRF. And that's really what determines your Doppler velocity measurement. So, Doppler velocity. Also known as radial velocity, people call it that sometimes too. Depends on who you're talking to. And the reason people call it either one of those two, Doppler or radial, is because you're only measuring a vector. You're only measuring you're only measuring the velocity along your beam. So anything that's perpendicular in the extreme case, you don't measure it. And then, depending on how much of it you're sampling, you get more and more of it. So again, if you're 100%, if you're 90 degrees, you're perpendicular, you're not seeing any of it. It doesn't mean it's not there, you're just not measuring it. But as you get more and more closer to 100%, more and more closer to parallel, you get more and more of the true wind. And these are just several ways to look at this. So again, your radial component, if your total velocity is going that way, you have a component that way and a component that way, but again, you're only seeing this much. And then this, which is a little blurry, if you have a wind blowing from left to right, up here, you're measuring all of it, down there, but up there, you're not measuring any of it. Because if these are your radar beams, you're at a 0 degree angle to that. And again, just depending on what fraction you're at, depends on how much of the actual wind you're really measuring. All right, Doppler velocity. But as everybody always puts in this caveat when you talk about Doppler velocity, it has Doppler in front of it, and it is a Doppler velocity, but that's not actually how you measure it. The reason you don't measure it that way is because this shift, this Doppler shift, when people think of Doppler shifts, you think of your train example, you think of astronomy. That's actually a big proportion of the shifting of the wave. So it's actually a large number. It's a large part of what's happening. But when you're dealing with weather targets, it's the teeniest, tiniest, smallest, littlest bit, and your electronics can't do that. We're not good enough yet. Our chips aren't fast enough, and we can't quite do that. But the thing you can measure is you can measure the phase shift. So you can measure how much the phase shifts between the signal you send out and the signal that comes back. And by measuring the phase shift, you can get the Doppler shift and the Doppler velocity. So you're truly measuring a phase shift, not the actual Doppler velocity. And just one other thing, you don't actually even measure this quite 100%. I mean, you do measure it, but you don't measure the true signal coming back because it's still really, really, really tiny. What you have to do is you have to mix it down. You have to make it a larger signal. So you mix it with lower frequency stuff in order to do these estimates. So it doesn't come back, it comes back like this, but it's mixed with what we call an intermediate frequency or down converting, and then you're able to use that frequency, and then you're able to understand what the phase or the Doppler shift is. So there's the dirty secret of Doppler velocities. I think I sort of said that. This was just an example in a tornado, and I'll show much more of these later. But again, you have your zero dot line. Again, doesn't mean the wind isn't happening there. It just means you're not measuring that component. But things you can see sometimes is you can see convergence and divergence depending on what your zero dot is actually doing. So back, again, Doppler velocity. People who study tornadoes, people who want to look at tornadoes, want high Doppler velocity. They want something called a high Nyquist interval. You want to be able to measure winds that are really, really fast. So I'll call that Vmax, the maximum wind speed you can measure, and not be confused about what you just measured. So the first thing is it depends on the wavelength of your radar. So these are different radars that operate in the world. So W-band and Ka-band, those are usually what we call cloud radars, and there is an exception at Texas Tech, but those are smaller wavelength radars, so they're 1 centimeter or millimeter wavelength radars. So with smaller radars, you're not able to measure as high of a velocity because the highest velocity you can measure is dependent on the wavelength of the radar. As you get bigger, as you get into X-bands, DOWs, NOXPs, MAXes, sort of your other research radars, you're getting better. C, you get a lot better. And then with S-band, with the 88D, you're even better then. So these are able to measure higher velocities without doing anything funny than your W-band type of radar. So smaller wavelengths filled more. So a lot of people that operate radars, especially when they're operating them in these smaller bands, and I won't get into this in great detail, but we could talk about it later if you want, they do different sorts of mitigation techniques. There's something called a staggered PRT that people do, which means they actually send out 2 different PRTs and are able to then get a higher velocity measurement. And the 88Ds, at least the Canadian 88Ds do something similar to that. They send out, I think, a different PRT each beam or something. So there are ways to mitigate this problem with your wavelength in your radar. You could do these sort of fancy processing or fancy transmitting things in order to get higher velocities. And just to illustrate, I kind of still like these diagrams. What I'm talking about is, again, you can only measure a velocity up to a certain amount, and Vmax, whatever you want to call that. Like I said, people call that the Nyquist a lot of times, where you say it's folded. And what that means is if you could only measure up to 25 meters per second, for example, if your particle is actually 30 meters per second, what it does is it wraps back around, and then it wraps back here, and then it wraps 5 meters per second inward. And because you've exceeded your Nyquist velocity. So it just wraps around. So you can see in tornadoes, and if you have a bad Nyquist velocity, what could happen here? This is pretty unambiguous, and I'll show you examples of this. This is pretty unambiguous if you see 30 meters per second. You're usually sort of looking at a smooth transition between your velocities that it wraps back around to 20 meters per second. But if you have small Nyquists, and sometimes people do, your Nyquist is 5 meters per second, those wraps can keep happening because you can only measure so much. So it can go back and back and back, and instead of unfolding it once or trying to, put that there, you have to figure out what is going on because it's no longer decipherable. And people still do it, but I'm just saying it's a tricky thing to do. So if people have folded velocities, and especially if they're folded a lot of times, those are velocities you should wonder about what went into unfolding them to get those type of velocities. So FYI on maximum velocities. So just showing you and just grabbing it from the 88Ds. Everybody, I think, knows what folding looks like. This is some tornado. But when you see it in the radar data, what you see is these colors. So we indicate things by colors. Like I said, you're just making a pretty display here. And you start seeing in here, you were green, but now you're red and you're orange, which means we're at minus 16, but then suddenly you're at 24. So you didn't suddenly come across some weird shear zone, you just folded your velocity. And a lot of times the folding is pretty smooth. It's not like some crazy thing just happened. And you can see that in this. It's a pretty smooth transition to these folded velocities. Again, it can be challenging unfolding velocities, even when you have one fold, or if you're not well sampled enough. If you're not sampling your tornado well enough, sometimes it's challenging to unfold it too. And this was Dodge City. A lot easier to see this fold too. You know, your green, 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 you know, minus 16, and then suddenly you come back here to the 23, plus 23. And again, you've just folded your velocity because your radar couldn't measure a velocity higher than that. Oh, Dodge City, just because it was sort of cute. Other things that you see in velocity, and especially since this is close to the radar, you can see a lot of times ground clutter. There's more better images of this, I just saw that. But when you see these sort of relatively straight lines, a lot of times with zero velocity, those aren't, you know, along your zero dot, those are usually streets. So you're usually looking at power poles and stuff like that. And you can see that a lot of time in clear air. When these clutter targets, when these things don't move, you're just looking at something that's in the ground. Also variance, again, still in this Doppler discussion. People use Doppler velocity. They use this, they use spectral width, again, which is your variance in Doppler velocity, in several different ways. So first of all, I'll just say it depends on a lot of different things. It depends on variation in fall speed of your scatterers. So if you have different scatterers falling at different speeds in your radar volume, that can affect your spectral width because things are broadening. There's different velocities that you're measuring. Turbulence, if you have a lot of turbulence, that can affect your spectrum width. In tornadoes, a lot of times, you get a high spectrum width because it's very turbulent. Vertical wind shear, and then also just actually the motion of the antenna could affect that. So a lot of times when people are trying to back stuff out, they sort of ignore 1 in 4, just because it's hard to account for those and that. So the top one is something would have a large spectral width, and the bottom one is an example of a small spectral width. So again, instead of also looking at just turbulence, the other thing people do sometimes with spectrum width, because it's a variance, so it's reported in velocity units, sometimes people look at their highest spectrum width, so their highest value that they got, and they think, oh, my velocities could have been this high. So just say, for example, you're measuring velocities again of 25 meters per second, and you see your spectrum width has some variance in there. So you see spectrum width, say, of 3, 4, 10 meters per second. Sometimes people look at that and they say, oh, well, I can add 10 meters per second to my velocity because it's possible in that volume that I'm sampling, since there's a spread, 35 meters per second might be a higher velocity. So it's more of just an FYI of what sometimes people do with spectrum width, besides just looking at turbulence. They sometimes use that to look at what the range of velocities they sample could actually be. Right, more spectrum width. Just checking on time and getting everybody to food. More examples of spectrum width. Dodge City, sorry, I keep pulling Dow stuff too. Tornado, high values of spectrum width. Other parts, shear zones there, you're also seeing high values of spectrum width. You have a lot of shear, you have a lot of turbulence going on. Doppler dilemma. Talked a lot about Doppler velocities and really wanting good Doppler velocities that you could see really, 100 meter per second ones. And you have a problem with that, is that if you want to see it 100 meters per second, you'll get a smaller range. So as far out as you can see is mitigated by your PRF. So if you increase your PRF, do it at a faster frequency, what happens is you decrease your range. You decrease how far out you can look. So that's called the Doppler dilemma. And it's also wavelength dependent, so it depends on the radar. I grabbed this, 10 centimeters, just FYI is, your 88D. 5 centimeters would be your TWR, your airport radars. So if you see, for example, if you wanted to look at 100 kilometers, your 5 centimeter radar, you can only, see about 19 meters per second. But with your 10 centimeter radar, you can see about 35 meters per second. It's wavelength dependent. So again, when you work with these smaller wavelength radars, you're trying to do a lot to mitigate some of these issues. The other little tidbits of things people want to know, maybe not. Rally versus me scattering. So when you talk about reflectivity, which I have to tell you, is probably the worst variable in the world. It's probably not well calibrated most of the time. Everybody just wants a reflectivity that looks like an 88D reflectivity, but it's very hard to calibrate. So just FYI, it's a funny measurement, or it's a funny equation to get a measurement. But what you need to do, though, in terms of getting reflectivity, is people assume it's in something called the Rayleigh scattering regime. And all that means is basically this picture here. So 10 centimeters, again, that's your 88D network. Things that are raindrops, snowflakes, they're all smaller than that. They're a tenth about of the size of the wavelength. And that's what your reflectivity equation is based on. But once you start getting larger, if you get really large hail, you get pieces of debris, and you start getting close to the size of your wavelength, you get out of this Rayleigh regime. You get into something called the Me regime. And really, that's just not what you're using when you're deriving reflectivity. So that's an FYI there. Again, since this is wavelength dependent, you also see the problems with smaller wavelength radars. X bands, W bands, KA bands, they get out of this Rayleigh regime pretty quick for their reflectivity because they're very small wavelength radars. And then I was trying to find an example, but I couldn't. But C-band, because sometimes hail can be about the same size of the wavelength of the radar, and you get something called resonance. You get some pretty funny answers when you see hail sometimes in C-band, because it's in this weird regime, which is not the Rayleigh regime. Again, I sort of said reflectivity is a little bit of a bogus quantity, but with that said, in the Rayleigh regime, it's basically dependent on the number of particles, the number of things you're scattering off of, but also the size of them. So bigger particles, d to the sixth, come into the reflectivity, or weighted more in the reflectivity. So this is just a quick example. This radar volume and this radar volume would have the same radar reflectivity value. This has a lot of small stuff and a couple medium-sized ones. This has not much, but a lot of big stuff. And again, d to the sixth impacts your reflectivity more than the number in that case. The other thing with reflectivity, and sorry I keep pulling Dow examples, but they're good examples, is you can get something with attenuation. And you can get full attenuation, or you can get partial attenuation. So shorter wavelength radars again, I know I'm not really doing a good job selling shorter wavelength radars, but shorter wavelength radars again, they attenuate faster. So instead of getting the energy scattered back to the radar, more and more the energy gets absorbed and scattered away. And what ends up happening is when you look through something like a hail core, like this, you see this region right here, you're missing a chunk of the reflectivity. And that's because it got attenuated. If you compare that same one to a C-band, you see that you do get some attenuation in the C-band, and you'll probably see that in S-band too, but you see you don't get that big chunk missing because it's a longer wavelength radar and they don't attenuate as much. The other quick example here, also reflectivity, you can see that both of these radars are looking at the same storm, Goshen, and you can see they have different reflectivity values. So sometimes looking at, again, absolute reflectivity values is a little bit of a bogus thing to do. Also, I'll come back to that. I'll come back to that another time because I have 1 minute and 35 seconds left. Also, just quickly with attenuation, again, not trying not to sell small wavelength radars. This is an example in a hurricane. You watch the hurricane and all this here. See that? You just lose your whole velocity field and you lost your whole reflectivity field. And that's what happens when you're an X-band radar and you're going through a lot of rain. So you can see it does good in other parts, but once that eye wall hits, it just goes almost to nothing. So a lot of times in hurricanes, we're not looking out much more than 5 or so kilometers because we're so attenuated. Continuing on with radar. All right, we've gotten through our basic Doppler radar, and now we're going to add the second polarization. Very exciting. So I'm sure, as everybody knows, as of, 2012 or something like that, most of the 88D or all of the 88D radars now are dual polarization radars. So what does that mean? That means exactly what it says it means. That instead of just transmitting in one polarization, it transmits in 2 polarizations. So it has a horizontal component and has a vertical component. And what that does is that allows you to tell you something about the dimensions of the particles or the volumes that you're looking at. So things like, things like hail sometimes have a larger horizontal compared to vertical. Also, actually, sometimes they're pretty close to the same. So they scatter back pretty equally. But other stuff like snow usually has a more horizontal dimension, less vertical dimension, so you get a lot more horizontal scatter and not vertical. So the new dual pole variables you get is something called, and I'm sure you're familiar with most of these, ZDR, or differential reflectivity. In theory, it's just the difference between your H reflectivity and your vertical reflectivity. Other ones, rho-HV, that one I'm sure a lot of people are familiar with because you look at that a lot of times when you're looking at debris signatures. And rho-HV is just looking at the correlation, as it said, well, people call it correlation coefficient, I should say that. So if you hear correlation coefficient or rho-HV, it's the same variable. A lot of times, I don't know, for some reason we call it whatever. I don't know why. We call it rho-HV, but then other people call it correlation. But correlation is probably more descriptive because it is the correlation of the return power from the horizontal and the phase of the horizontal compared to the return power and the phase of the vertical. And that's your correlation coefficient. And then other ones that I don't use pretty much ever, but people who are doing a lot of microphysics, looking at stuff, there's something called FDP. I'm not even sure if the 88D gives you FDP. It might just give you KDP. But FDP is how the different waves, how the H and the V propagate differently through rain or through hail or through different types of hydrometeors. So the difference between those propagations. But then what people really look at a lot is something called KDP, which is basically how that happens with distance. So you're really looking at the range derivative of your FDP. And like I said, I don't use those much, but people looking at precipitation stuff too. So there's different ways to do dual pole. And the way the 88Ds do it and the way a lot of research radars do it is they do it at what's called a 45, it's called slant 45. So that means they transmit both H and V at the same time. So if you're slanted 45, that means you have a vertical component and a horizontal component because you're at a 45-degree angle. And in theory, those are equal because it's a nice triangle there. And that's what most radars do, is they just transmit slant 45 and receive back from that. And what you get then is you get back what we call co-pole products. You actually get back the V compared to the H and the H compared to the V. Other radars, and there's not many that do it this way, they do something called fast alternating. And I think only a couple of radars do that, a couple of research radars do that, is basically they transmit horizontal and they have a fast switch and then they transmit vertical. So they do a fast alternating. That switch is kind of pricey and really expensive to do. So I really think only NCAR's S-pole radar might be doing fast alternating. But what all these things do, you could do a few more products with that one, but products that are a little bit exotic. So a lot of times what we're looking at are the cross poles, but then sometimes we look at how the co-poles also vary with each other. The Dows, on the other hand, the Doppler on wheel radars, they also have some sort of special way of doing it. What we do is we transmit at two different frequencies, two different X-band frequencies. One of those is slant 45, but then the other one we transmit at as just horizontal. But what we see when we get back is we look at both the horizontal and the vertical receive. So we sort of do something that gets us close to what those other, that other research radar is doing. And that's probably the advanced, that's the end of the advanced portion. I promise after this it'll get more fun. So again, I think a lot of people are familiar looking at these products. Again, I know, sorry, I keep using Dow data. Reflectivity, Doppler velocity, then you get something, you get your rho-HV. People are probably very familiar with this low rho-HV in tornado centers because your H and your Vs are not very well correlated. That means there's a lot of stuff in there that isn't the same. You see that in melting layers too, when you have a changeover from snow to rain. It's a lot of the not same stuff, so you'll get low correlation between your H and V return signals. ZDR can be interesting. ZDR, since it does sort of use power and reflectivity, it's also an interestingly calibrated variable because your power and your reflectivity have to be well calibrated. So I sort of look at relative ZDR, but presumably the 88Ds sort of all use the same calibration. So when you look at ZDR across an 88D, it's probably usually pretty consistent. The one thing, I mean, you could tell sometimes when it's not good. It'll be way high or way low, and you're like, oh, what happened to their ZDR? Because sometimes that happens as well. But for ZDR, sometimes you get low ZDR in the center of tornadoes, that, you know, your V is scattering more than your H, and I could show you this more too later. Sometimes you get places, if you've ever heard of the ZDR arc, where you have enhanced ZDR around supercells. That's indicating something about the droplets and also about the vertical shear in the storm. So people are using ZDR to actually look at some of the more, I'll say, properties of the environment in addition to the storm. All right. Oh, a loop. Okay, so looking at an 88D, I put a lot of slides together, and I can't remember if they're going to move or not. So I just want to show an example with 88D data. I showed you Dow data, but this was a tornado somewhere. But basically, what we're doing, in case you're wondering, we're just keeping the tornado centered, so that's the reason it's not moving. So in reflectivity, just to talk about a couple of things you're seeing. You're seeing a debris ball there, so you're seeing a really high area of reflectivity where the debris is. Correspondingly, you'll see low rho HV because there's debris. There's not a good correlation between the H and the V return because there's a lot of mixed things in there. And ZDR, you will see the ZDR arc at some point there where you see sort of this higher ZDR where you have a lot of H. You get a lot of return from the H as compared to the V. The one thing I will point out, and I'll say this momentarily what this is more, in velocity, of course, you can see it's horribly, terribly folded. And that's 88D life. Watching again. So you also see this little spike that comes out. And I'll talk more about sort of three-body scattering, or I'll talk briefly about three-body scattering, which you can get from hail, but you can also get that from debris, too. So that's also indicative that you might have debris there as well. So you might have large hail, but debris can also produce that spike, I don't know, along the radial by the tornado. I'm trying to think how to describe that. So again, this is just putting a couple things I said into pictures, because pictures are always better to me than words, or one of these will work. So this VDP I talked about, which I said is the propagation difference as it goes through a medium between the H and the V. So something like this has a VDP of some useless number, it's in degrees. But something like this would have a higher concentration of raindrops, so there's more of a delay in the H than the V. So you get a higher VDP than you would get for something like that, when your H is being delayed more than your V is. Similarly, something like this, you can see that those will also have different VDPs. But VDPs alone are hard sort of to look at because they're cumulative. They don't reset themselves. That's why they do a derivative with VDP in order to get KDP. And so VDP, range, and you can see you have low VDP. You go through a medium, your VDP picks up, clear air again, it's straight, but you don't start back from zero here. You go up again when you hit that medium again. So it's cumulative. So what people do instead is they just look at the range derivative. So as you go along that, this would be something similar to this. So VDP versus range, straight line, high correlation coefficient, low diversity of hydrometeors, VDP versus range, low correlation coefficient, high diversity of hydrometeors. And again, your KDP is just your black line that goes through there. Three-body scattering, I promised I'd say something. So you see something similar here. A lot of people think of it again with the hail spike. I couldn't find a good picture of this, so this is what you got. But basically what's happening is you're sending out your radar beam. It's hitting hail. It might be hitting debris. Reflects back to the ground, reflects back to the hail, reflects back to the radar. So you get three-body scattering. You get three different scatterings or multi-scattering going on. And the way the radar sees that is it doesn't see it happening at quite the right place and quite the right time, so you get that hail spike that comes out, because that's just the way the radar is interpreting all these different scatters before it gets back to the radar. So again, here's the example. You sort of have low reflectivity a lot of times with these three-body scattering. You'll have low correlation coefficient because it's kind of a garbage scatter. And then velocity also, or not velocity, ZDR also might be pretty garbagey. So that's your three-body scattering. This isn't, I just do this thing because it's fun. I always see these on 88Ds, and people are always asking about bistatic coupling. Basically, I'm sure you've seen it, where you see the other 88D. So some other radar, and it's usually the 88D, is pulsing pretty close to the radar that you're with, and that signal is able to be received by another 88D. So people call them rabbit tracks or bistatic coupling. That's what it is when you see there. And you'll see also, in that case, the velocity that doesn't even translate. It's garbage usually in this bistatic coupling. All right, side lobes. Moving through this advanced part fast. I think I alluded to before, remember main lobe, you have your 3 dB beam. That doesn't mean that there's not other stuff outside of it. So there's this other stuff outside your 3 dB beam called side lobes. So there's energy still spilling out of your dish. And just reminding you that it's not 2-dimensional, it's 3-dimensional, so it's spilling out in all directions. And this was sort of a tricky one to find a paper on, or sorry, find an example, so I just stole from a paper. But I'm sure people have seen this, and I definitely see this conversation going on Twitter when you get this side lobing. So what happens, because you're spilling out energy, if you're spilling out energy and it's hitting higher reflectivity stuff that's coming back, sometimes you're seeing something that's going on a loft as opposed to what's happening at the surface, because that other part of the beam has actually made it back to the radar. So I think the example a lot of times people show, and again, this is actually a really good paper if people want to look it up, about radar side lobing and 88D side lobing. So you see these vortices, or what looks like a vortex, or it looks like a strong circulation, and there's no real reflectivity associated with it. And usually your cross-correlation coefficient, your rho HV, will be pretty low with that as well. So it's just something to be aware of when you're looking at radar. That's what's happening. You're just getting some scatter back from the side lobe, not the main lobe. And again, usually at a different height than what you're seeing at your height. Okay, 2 more things. 2 more. Okay, real quick, also stealing from Kunjin. Also a really good paper if you want to just look at stuff. He explains things very well. Some other weirdo artifacts that you get. You get something called differential attenuation sometimes, which means we talked about attenuation when things travel through the media. Sometimes they get absorbed and they don't really get back, so you start losing your signal. Sometimes the H and the V are different, so you get something like that. You get these differential attenuations usually behind sometimes these hail cores. The other thing you can get is and this is happening more with non-uniform beam filling. So your beam, again, this conical beam is coming out. It's supposed to be filled with stuff all uniformly. Sometimes that doesn't happen. Sometimes your beam isn't uniformly filled, either with stuff or it has mixed precipitation, debris, and other things in there. So it's called non-uniform beam filling. And you'll see streaks out of that with your rho HV a lot and your VDP as well. And depolarization. Last weird artifact. Is that sometimes when you have a good electric field going on in a thunderstorm, the way the crystals arrange themselves up near the anvil at the top of the thunderstorm, and this only happens when you send out a 45 slant. It doesn't happen with the other type of radars, but since the 88D is the 45 slant, what you get is you get these ZDR depolarization streaks because of the different ways that the H and V, it's random reacting to these the canting of the ices. Okay, now. I promise this will be a lot lighter and a lot faster, so Gabe can get up here quickly. So what I wanted to switch to, that's sort of radar stuff. And if people have questions, I didn't touch on phased array. I know people had asked me about phased array. Certainly, there are research groups working on a lot of phased array radars down at OU. Also, NCAR is going to be working on a phased array called APARS, which is going to go on an airplane that's supposed to be ready in 6 years, 5 years. So there's a lot going on with phased array radars. And some of the good things about phased array radars is that you have no moving parts in a lot of these phased array radars. So big clunky 88Ds, big clunky DAOs, they have big motors, they have big stuff that could fail. Phased arrays are all nicely electronically controlled. There's also a lot of nice electronic processing that goes on with that. And they scan fast. So those are all good things. Bad things are they're expensive. And even some of the research radar phased arrays, they actually have very bad, I'll say, beam resolution. So they don't necessarily have your nice 1 degree beam. They usually have 3 degree beams or something like that associated with them. So their azimuthal resolution isn't as good right now. Those are the goods and bads in phased array. I mean, I think phased array is at some point going to be pretty prominent in what we do, but it's also pretty expensive at the moment. And in terms of getting your bang for your buck, I think at the moment still these these scanning radars, for the most part, are what most people are trying to use. So I just want to talk about using radars for research. Radars are used for all different sorts of research, and supercells, tornadoes, MCSs, squall lines, bow echoes, CI, you name it. Research radars are out there trying to study these type of phenomena. So besides being, an 88D, and having an operational network, what's really exciting about these research radars is you can get different types of measurements. So why use radar? Obviously, all-knowing, all-seeing. The 88D radar, of course, was made to be all-knowing, all-seeing. It's made to give us good coverage over a broad area. That's great for operational uses, not so great for research because you can't see close to the ground sometimes. Well, X-rads, places you can see close to the ground, you sort of get goodish 2 or 3D coverage. They scan quicker now. A lot of times when you're in a storm mode, they do, these revisits to the low levels because the low levels are important in forecasting. So they switch between the different modes, trying to optimize it for whatever type of weather that you're looking at. So again, they're pretty good for operations. But if you're actually wanting to get any sort of scientific measurements, it's a targeted rare phenomena, a tornado. Even the 88D, I'm watching it here. I know, the tornado that should not be mentioned. But I'm watching it here, and it's horrible. It's so far away, it's just gross. It looked good for a bit, but what I really want out there is a mobile radar to look at and see what's going on in the storm. So again, you just get close with mobile radars. People are putting them on all sorts of things. Actually, CSU has one that goes on a boat. So people are trying to get a lot of different places with these mobile radars. Examples of lots of billions of mobile radars. A lot of people have radars, different wavelengths, different frequencies, different dish sizes. And I feel like I did a really poor job selling selling X-band radars. I told you how they attenuate, how they're Nyquist. You have to work to get it better. But there's a lot of good reasons that people are using X-band radars for mobile radar research. So attenuation versus resolution, again, you just have to decide what you want to study. In order to get good beam resolution, in order to get a 1 degree beam or less than a 1 degree beam, you need a dish that can do that. So if your wavelength gets big, you need a bigger dish to do that. That's also true about phased array. You need a bigger aperture to do that. So in order to get these resolutions with longer wavelength radars, you need big dishes. So obviously the problem is getting these dishes down the highway for mobile radar research or other types of research. So people have sort of settled on these X-band systems because you can get a 1 degree beam width, which is what our 88Ds have, and you can get your truck down the road. Again, that doesn't mean other people don't have different wavelength radars, and these are just some examples of different people who operate these different radars for different reasons. So I'm gonna go quick. All right, well, actually, I just want to go a little history with radars. So again, trying to actually get mobile radars, and this is from the Thunderstorm project. Oh my gosh, back in, 1947, that was a radar. But really what ended up happening in a lot of these different institutions, a lot of these different schools, they wanted their own mobile radars. So I have my cute little timeline, or not cute. But really, in 1990, Howie Bluestein at the University of Oklahoma had a CW radar to study tornadoes. He also then had a W-band radar in conjunction with UMass. So again, a very small millimeter wave radar, but it was easy to get down the street. And then really, until the Dows came along, there wasn't this sort of pulsed X-band 1 degree wavelength radar. So there's the picture back in the day, courtesy of Herb Stein, but that's what his continuous wave radar looked like. And as you can see, you don't get these pretty pictures. Basically, you're seeing sort of lines and trying to figure out exactly where things are when you look at that. So Dows, again, we're trying to put a regular radar on a truck. So it's not too much of a lie to say that sort of went together to get that. And that was the first, Doppler on wheels. I don't know where it exists now. But you also notice it has a smaller dish, or maybe you won't notice, but it has a smaller dish than the Dows do now. It's also on a pretty underpowered truck. That would be hard to get up hills. But Dows and Vortex 1, these were really the first mapping of tornadoes, like you think of mapping of tornadoes. And these are just screen dumps, but again, pointing out, you can see there's, folding going on there in the radar. So skipping ahead slightly, there's also in Vortex 2, Eldora, the Eldora X-band radar, which has been retired. But like I said, NCAR is working on a phased array C-band radar. It's tail radar. NOXP. NOAA has a tail radar, and sometimes you see that in hurricanes too. So their radar is, sitting in the butt of the tail, the butt of the plane. But you can get really great I don't know what you call the back of a plane. I'm sure it has a name, aft, starboard. But you can get great cross sections through. Just making a point real quick with airborne radars. I mean, first of all, there's only so many places the pilots will fly these airborne radars. So that was part of the problem. There was supposed to be some big A-10 hail penetrating radar years ago that was supposed to happen, and the pilots are like, hell no, we're not going to do that. So there's always that problem that people aren't going to fly in places that you think you want them to fly. And then also, it's hard to see near the surface. You're not really seeing near the surface in these airborne radars because they're scanning off from space and not space, but they're scanning off the air, and you're not seeing close to the surface. Also, I was just when you want one truck, you really want two trucks, and you really want bigger dishes. So 2 radars can get you something called dual Doppler, which you can't get with one radar, if you remember from just an hour ago. No, we were talking about Doppler velocity being Doppler velocity, not being a real wind measurement unless you're right there. Unless you're actually measuring it parallel. But if you have 2 radars, you could actually construct a real wind measurement. And it's something called a dual Doppler or multi-Doppler analysis. And the idea is basically that you're looking at what you want to resolve from 2 different angles. So one radar resolves it this way, and one radar resolves it from this side, and then you combine those magically. No, you combine these through math, and you're able to actually get vectors. So you're actually able to get, what you normally think of when you see wind, something like that, 8 vectors. You could also integrate and use convergence and divergence and see what the winds are doing, what the ups and downs are doing. So once you get vectors, there's a lot of different things you could do. And sort of in the phased array area, we have this rapid scan dial. And like I said, all these mechanical radars, they do a loop, do a loop, do a loop. Dow scan, pretty fast. We could do one angle at 7 seconds. OU has a radar called Raxpol that if you've ever seen that out in the field, that whips around pretty fast. I think it's seconds, and they can do one skip through. But what you want to do, again, is look at different angles a lot of times at the same time. And that's the phased array problem. People want to look at different elevation angles and not watch this, and then this, and then this, and then this. For fast things like hurricanes, tornadoes, things are evolving really quickly between those different scans. So this is the rapid scan dial, which is sort of a poor man's phased array. It's a passive phased array using basically the waveguide to steer it. And I'm holding this. Okay, so that's not moving. I'm going really fast through. Just want to show you this sort of cute thing. Well, I should say one of the first dual pole measurements with mobile radars, and I know 2012 is when our 88Ds became dual pole. Down in Oklahoma, Bluestein really with one of their radars were some of the first few people to map out these signatures that we now recognize in the 88D data. So this is sort of a really cool illustration I just like to show in terms of changing of parameters. Happened a long time ago. This is Canton Lake. But what's really exciting is this is all lake on this side. The other side is forest. So if you watch reflectivity, you see you got your clear eye there. And as soon as you hit forest, boom, you got a debris ball there. So really, concrete evidence of, debris ball and dual pole data. And again, with your debris ball, you're also getting this low rho HV, this low correlation coefficient, because you have debris. You have all different sorts of scatterers out there. Now, I feel like radars have multiplied like rabbits. So everybody has a radar these days, and they all are uniquely different in their own way, and that's actually a true statement, because a lot of these radars are custom made, other ones are from companies, so probably no one of these radars are exactly identical except if it's the same person operating it. So we have a lot of Dows. Now we have 3 of them. And you can sort of read through this list of different people and different radars. And I'm probably not even up to date because this OU air radar is now gone. And there's a new OU phased array radar that's replaced it. Real quick, I just wanted to do a shout out to the Texas Tech KA band, short wavelength radar. So attenuates a lot, has low Nyquist a lot of times, but again, you can mitigate that. But what's really exciting about that is because it's a small wavelength radar, they don't need a big dish. So with their dish, they can get a 0.3 degree beam. So I'm talking about these 1 degree beam dishes. Texas Tech can actually do a 0.3 degree beam. So much better angular resolution with these smaller wavelength radars. Again, with all the caveats, which is usually they attenuate a lot behind anything other than the tornado and the gust front. What can make radar observations better? Obviously, more radars, more wavelengths. I just want to talk a little bit minorly about sciences. And people ask about projects all the time and what people are out there doing. Certainly, there's a lot of these big projects that go on. The latest one, I think, was Perils when we were out in the southeast, where there's these big multi-agency projects, lots and lots of people out there, lots of instruments out there, which is great. But one of the bad things is that your data collection is usually a lot limited to like one season. That's usually what all you get funded for. And with all those multiple people comes multiple objectives. So these projects end up being very diffuse. So even though it's a big project with a lot of people and a lot of stuff, it's harder to get your particular objective satisfied in these types of projects. That's why smaller projects like Rotate, Twirl, the ones we talk about, Team Dow, OU, they usually sort of do an annual project. Texas Tech, I think they're going to be out this year too. And the idea with these smaller projects is that you have less stuff, less people, they cost less, but you can go out a lot more often. So you can go out a lot more years and get a lot more data. Not with a lot more stuff, but you aren't limited to yourself to one season. Okay. I'm looking at Gabe, sorry. How much time do you have? Oh my God, okay, then I'm gonna talk really fast. And everybody's asking about this tornado. I think this is the one up in Nebraska, Benkelman. All right, so this is getting into more weeds of mobile radar. So it's advanced, but more interesting. So again, basic radar measurements of tornadoes, and again, this is gonna be very tornado focused. Here's your radar, your pulse width, gate length, beam width. See, we've been through all this stuff. But really, when you're doing a lot of the science, and coming back to the science, here's your house. You're usually sampling above your house. So just reminding people that you're not actually usually sampling at house level, unless you're pretty darn close. But again, you're usually sampling over the house. Also, again, because your beam width spreads and the height that it goes at, the farther away you get, the range varies. So if you're 10 miles, if you're 10 kilometers or 6 miles away from the tornado, you're already looking up 80 meters. So just reminding people where you're at in these. So ideally, you'd like to be in the 1 to 2 kilometer, with the mobile radar range in order to get the observations that you really want, because you start to get pretty high up when you look at these other ones. The other thing, too, to note with mobile radars, and not that it doesn't happen with other radars, but especially mobile radars, you're blocked by a lot of stuff. So people think they're measuring lower than they are, but they're actually not. Because what happens is you send out your beam. So here's your beam. Here's your 3 dB beam. Hits a tree. Tree blocks it. Hits a house. Blocks more of it. And what ends up happening is really your beam is up here. So most of the energy in your beam is higher up than where you thought it was. So blockage in these cases, too, could shift the height of where you're actually taking the measurement because your energy is higher up. Other people, and again, if you want to read, Jeff Snyder has a good paper in 2014 who talked about a bunch of this stuff as well. I'm going to go really more here. I feel bad. I want to talk more about tornadoes. Okay, because I do want to talk about this. So tornadoes come in all different shapes and sizes. If you've been here, we've said this a lot of times. And the one thing we talk a lot about is multiple vortex mesocyclone, this MVMC. And I'm bringing this up for a reason. And again, these are all different types of tornadoes, different types of structures. A lot of times you don't see that singlet velocity structure. And you get interior vortices, you get all sorts of vortices. But what I want to talk about really quick is El Reno, because, I don't know, I've talked to Ed, but, and an example of an MVMC, because this is something that we're starting to see kind of commonly in our radar data, and it's a challenging thing for us, but it's probably also a challenging thing out there as a chaser. And I don't know how you necessarily see it in radar data with the maybe AD, but I just want to just talk minorly about this. So these MVMCs are basically circulations that are probably about 2 kilometers wide, but you have vortices embedded in there. And this has been a big discussion of what exactly is a tornado. And we have this discussion a lot. So we've come up with the definition of a tornado that doesn't mean it's a tornado. It doesn't mean that anything 2 kilometers wide or larger is not a tornado. So putting it in words, and again, this was from 2013 that we did this, but I'm bringing this up again because of this big discussion. So obviously it's a little radar-centric, but we're looking at things that are usually less than 2 kilometers, so between your maximum winds. We're looking at things that are 40 meters per second. That's sort of been our threshold, a delta V of 40 meters per second. That means the difference between your inbound and your outbound velocity. And we're looking at that to be about 40 meters per second. Yes, can things at 39 or 38 meters per second still be a tornado? Yes, but things usually when they're 40 meters per second, they're a tornado. You know it and you've seen it. But it's not embedded in or within 2 kilometers of another vortex. So that's sort of your tricky part there, right? Because what do you call a tornado when you have multiple things going on? So this has been our sort of working definition of a tornado, and that's why we bring up this multiple vortex mesocyclone. In this case, you have multiple vortices within these broad circulations. So there's not just one vortex necessarily on the ground or looking at. There's possibly multiple ones of these. So El Reno, and I'm going to go first with the 88D, and this is El Reno 2013. So watching that go again. So certainly you can see the hook there. You can see your low rho HV. And if you're looking really good at this velocity here, it's very broad, strong on this side, really strong on this side. It's kind of a mess, right? I mean, I don't know what I would think looking at that when you're looking at the 88D. What do you do? What's really going on when this thing breaks down and you have all these multiple vortices? So hold on one more second. There. Do you see that? You see when it does that? Yeah. So that's complicated. And I have to say, I mean, there's a lot of things we see on radar that we're not really sure what's going on. The experts, don't always, have the expert answer to stuff. And that's fine. I mean, we debate about stuff a lot of times. So it's fine not to, it's fine to look at something and not know what's going on. But, sometimes you have to decide what to do in that case. So this is the Dow data. We were out that day, and we were having a tricky time with this tornado. We didn't know what to do with it. So here's the vortex, and you see in there, you see that we didn't do it very well. These little loop-de-loops here. We had this little sort of cycloidal motion that forms. That was the vortex that ended up impacting the TwistX Maris's group. It was one of these little tiny embedded circulations. So you see there's this broad circulation going on, but within this broad circulation, there's another tiny vortex that forms and moves off really quickly to the northeast. So a very tricky, complicated structure. El Reno is not the only time we've seen stuff like this. We've seen this in other tornadoes, but in El Reno it was moving pretty quickly. Also, the Weather Channel was out that day, and the same type of thing happened there too, where you see not quite as fast moving, but you see there's a broad circulation, and in that broad circulation, you see that there's a vortex within it. So this is this idea of these MVMCs. And again, you see them, they're not unusual. We used to think, oh my gosh, what is this? But we've seen these several times now, and enough to categorize them and say something about them. So just, going back to this, that little multiple vortex, was moving really fast. It was moving, 80 meters per second. So the winds associated with, it's instantaneous winds associated with this were likely well over, approaching 200 or 300 miles an hour. And another group was out there, Rexpol was out there with their radar, looking at those types of winds too, and using their methods. They're getting similar speeds for these maximum winds. Other quick thing I wanted to show you, this is what it's like chasing with a Dow. And so you're going to see this all rotate and move around. This is Lockett or Crowell, Texas, 2022. So you see a lot of things going on here. So first of all, we're stopping and starting. We scan a lot when we're driving because a lot of times we're going into areas we don't have good visibility. We don't really know what's going on with the storm. The 88D data is not really very useful. So we're constantly scanning. So I just want to show you a couple things with this. And again, this is just more of a, this is what you'd be looking at as you drive. So obviously it's bouncy. So first of all, this stuff radiating out here, you see this sort of spiky stuff here and spiky stuff there that doesn't really have any velocity associated with it. And people are probably familiar with that. That's called second trip echo. So there's a storm or something beyond the radar range, and it's getting folded into this radar range. Usually your velocities are pretty crappy or incoherent in that because it's a second trip echo. The other things, you can see the ground clutter at some point, and the ground clutter moves because we're moving. So I'll see when you see that again. So all that ground clutter there, it's not actually moving, but you can see the ground clutter. There's places that were blocked. So when we're scanning through towns and we go by trees, we get blocked. And then the other thing that happens is we get pretty attenuated at one point. So the tornado goes away, or it's hard to see. Blocked. Hold on one second. Yeah, you can't see it. And eventually you're going to see the tornado again. All right, that's not it. Hold on. We'll do it again. But yeah, we get very attenuated. So driving. You see all these circulations there too along the knob. And then out back here, eventually we get attenuated. Well, anyway, sometimes that happens to us when we end up in a situation here, totally attenuated. You saw that went away to nothing? Because we're looking through the core of the storm. So that happens to us too a lot too when we're driving and we're looking through the core and suddenly we pop out and it's clear air and we see the tornado. So we look for what we call ghost tornadoes because sometimes there's some faint reflectivity there, but that's one of the big things that happen. And so people who are following us, by the way, buyer beware, obviously. And we're making decisions in real time about what to do. And there's certainly an active discussion. And there was an active discussion in this one because we kind of surfed through the inflow to get out of it. But we're watching this type of stuff and we're deciding what we think we could take and what we think would be appropriate for us to be in. And sometimes we see stuff that we think we can't get out of and we decide just to stop because that's the best answer. And sometimes we decide to keep going because that's the best answer. But like I said, there's your ghost tornado. And then it'll come back. There it is. See it? And then, yeah. So it never went away. It just got attenuated and you couldn't see it. Okay. And this is what it looked like. I mean, again, I'm just keep trying to show the 88D. So this is, what you're bringing up radar scope and you're having a horrible color tail because you're not in carbon 42. This is what your supercell looks like now. So same tornado, but looking at it now with the 88D. So different information, obviously, that people are looking at when they're doing something. I'm going to skip really fast to a couple of just new results that we have. So I could definitely let Gabe go. One of the things we've been looking at, this is 2023 results, is we've been looking at profiles in tornadoes. We've been trying to figure out what the winds do as a function of height. This is important for engineering and engineering standards. So recently, we published a paper in somewhere looking at that relationship. So what we did is we looked at all the tornadoes we had that had data under 100 meters. And then we didn't see much. It looks like a lot of spaghetti, right? We said, okay, what if we only have data under 15 meters? So what if we also had data, what if we additionally had data under 15 meters? Because not all these profiles had data under 15 meters. So what ended up happening is we got a lot less cases. But with that, what we see is we see a trend with approaching the surface, meaning that the stronger winds we think are happening near the surface. So this is another way of looking at it, which I like looking at. So this is just basically looking at the change in wind speed as a function of height. So anything here means it's stronger at the surface. Anything here means it's stronger aloft. So you can see that there's some relationship with winds, stronger winds occurring near the surface. So we went ahead and we published this profile using those very limited number of cases and making the conclusion, the in general conclusion that wind speeds are 31% stronger at 15 meters than they are at 100 meters. Now I'm saying that because people are taking that, taking those wind speed measurements at 100 meters and making them 31% stronger. We don't know if this result is robust yet. We have, like I said, a very, very limited number of cases. Most of those tornadoes also were pretty weak. So although there's some compelling evidence for this to happen and this profile to be true, it's really not, it's really not generalizable. So just, if you hear people talking about that, it's sort of been a thing where people have been making things 31% stronger at the surface. That's what's happening there. Okay, I'm really going to let Gabe talk because I could obviously go on forever. But I will end with one. Yes, I totally could go on forever, I know. Oh my God. Don't say it. Okay. All right. So people always ask, now what? And I sort of gave you that profile thing because the answer is more cases. Tornadoes are rare phenomena. Getting observations very near the surface is very rare. Just because you have 1, 2, 3, 10 cases, that's really not enough to make these strong conclusions. So, and I sort of touted the doing small field projects. That's one of the reasons you do these small field projects is you can keep going out and getting these specialized cases. So we've been saving the best for last. So if people see us out, we were out a little bit last year, but we'll be out more in full force this year. I'm doing the BEST project, Boundary Layer Evolution and Structure in Tornadoes. And what we're going to be doing is we're getting really close to tornadoes. I know, shocking. But with 2 radars and a small baseline. So we're going to have 2 radars doing sort of this dual Doppler analysis that I talked about, but over a really small baseline. So we'll have that, but we're also hoping to get low-level data. We dropped these pods, which people have heard about and we've talked about, getting surface temperature, pressure, wind data. What we're going to try to do in addition to that is, if people are familiar with these things called swarm sounds, these are basically soundings that are meant to be neutrally buoyant. So they're meant to go with the wind. They're called Lagrangian drifters, or I'm trying to think if you've heard about in the field. So basically what they do, people release 10, 20, 30 of these little balloons, and they drift with the wind. So we're trying to use these drifters to, I know, very ambitiously, get near the tornado and really map out the thermodynamics very near the surface in the tornado in conjunction with all this other data. We think the thermodynamics are very important, but without radar data, it's hard to put the thermodynamics in context. Without thermodynamic data, it's hard to know what's going on with the radar data. So it's a very synergistic thing looking at both of these. Also, hopefully going out and doing hurricanes for just cute names. All cute names should get funded. It's called Washable. So we're hoping to go out and look at hurricane boundary layer winds, which we've been doing a lot of, but actually really looking at it at the coastal interface. So looking right offshore, right on shore, and looking what those parcels of air are doing as it makes landfall. What else are we doing? Oh, lots of other things. Anyway, I'm going to end with the hat. Or else it's just going to go on forever. So thank you. And if people have questions, if people want to see other slides, I'll totally do it. But I need to stop talking.
All right. So advanced meteorology for storm chasers. This is one of my favorite pictures I've taken. This was the Sulphur tornado, May 9th, 2016. Probably the most photogenic wedge tornado I've ever seen. I think Hank Scheim is here. He's had a good look at it. Yeah. Hey, Hank. I think you had our vehicle in one of your views there. Incredible shots that you had. we were a little nuts, and I think Tim Marshall was even closer than us. So, it went away. So let's get into it. So you all have gone through this, so I'm going to skip over that. So we've talked about forecasting approach. Basically, we're going to look at supercells, forecasting supercells because they produce most of the tornadoes. Gone through the weather charts. I'm going to assume, in this case, that you absorbed at least some of what we talked about. There's going to be some stuff that's a little bit more high level. Hopefully, it all makes sense when we go through it. When we go through the supercell ingredients, you got your moisture, instability, wind shear, and lift. And then at the end, if we have time, I want to put it all together. Some of you probably have seen some of my talks about this, and I've kind of recapitulated some of the old stuff. And to be honest with you, I was ready to do something new, and so I've kind of reconfigured it, gotten to reading some new stuff, reading some journal articles, looked at a lot of stuff from Cameron Nixon. I don't know if you all have looked at Cameron's stuff. Just tremendous work with Hodographs. Cameron has done a tremendous job with Hodograph, so we'll look at some of that. Not in as much detail as he does, so I'd really commend you all to look at his. And honestly, if you all have a chance to look at some of Rich Thompson's stuff from Storm Prediction Center, he's got some really great stuff on YouTube that you can look up, and he does a much more detailed version of what I'm going to do tonight. So I'm kind of cobbling everything that I know together with what they've talked about, and then kind of not just talking about ingredients, but actually kind of going through the physical processes that these ingredients kind of lead to. So that's where we're going. All right, we've talked about this. Supercells responsible for 70% of tornadoes. That's why we're going to forecast them. And let's see. Okay, y'all know this. What do you need for tornado genesis? And this is incredibly simplified. And this is, I think, it kind of, after 3 months of looking into this, Eric called me, Eric Fox, called me in maybe November of last year and said, hey, do you want to do this thing? Or maybe it was October. And I said, let's do it. And so from that point on, I started reading as much as I could and looking at these presentations. And I thought, after all of that work, after all of the material that I read, it all came down to these two things: spin and stretch. And that's what you need for tornadoes. And you'll see how the ingredients for supercells come together to create these possibilities for spin and stretch. So spin, you've got the ice skater, she's spinning around, and then the stretch part, you can think about this like, she's bringing her arms in, right? That's why she spins faster, conservation of angular momentum. Same kind of thing happens with the circulation in the atmosphere. You bring that radius in, starts to spin faster. So that's really what you need. And that's what supercells do, is they put together these components. All right. So the ingredients are instability, moisture, vertical wind shear, and lift. So we'll start with instability. All right, steep lapse rates. I think it's really where it all starts is out in the desert Southwest. So steep lapse rates, what do I mean by that? A lapse rate is the difference in temperature through a layer. So we talked about in the previous session, the dry adiabatic lapse rate is the rate at which dry air cools as it's going up into the atmosphere. And so you can think about it like this. Okay, so say your temperature at 3 kilometers is 11 Celsius, and your temperature at 6 kilometers is minus 10. Okay, let me get through that and get to the math here. So lapse rate, in this case, is just measuring the difference in temperature over that distance. So you have 21 Celsius difference over 3 kilometers. 21 divided by 3 is 7. So that your lapse rate for that layer, 3 to 6 kilometers, is going to be 7 Celsius per kilometer. And I remember, I think it was Ryan Jewell. I don't know if you all know who Ryan Jewell is, but he's a Storm Prediction Center forecaster. And he always used to say, lapse rates above 8, tornadoes will be great. So just remember that. Lapse rates above 8, tornadoes will be great. So 7, okay, not bad. Not it. So again, a layer is the difference between two heights above the ground. So when we're talking about over a layer, the 3 to 6 kilometer layer, that's what we mean. The bigger the difference in temperature, the steeper the lapse rates. So think hot air balloon. You want that difference to be bigger, so that when your hot air balloon's kind of warm, you want what's outside of it to be relatively cold. And the steeper the lapse rate, the colder the air is outside the hot air balloon. And the closer to moist adiabatic, though, the weaker the lapse rate. So you want a bigger number. That's basically all I'm trying to say. The bigger the lapse rate, the better. Except if you get too big of a cap, but we'll talk about that. Here's a visual for that. This is one of my favorite cases. I love May 24th, 2011. That was my personal favorite outbreak. I don't know, there's something about a high-risk type of deal with from a meteorological perspective. Obviously, things did not go so well from a standpoint of people, but it was definitely just meteorologically such an impressive day in terms of CAPE and shear and so forth. You look at this sounding from 7 p.m. that day, and you see that 3 to 6 kilometer layer. That's what you see as about 7 Celsius per kilometer. So it's not overly impressive, but we had so much moisture, in the lower levels, 70-degree dew points, that it kind of led to quite a bit of CAPE that developed that day. So I borrowed these from Cameron Nixon. So these are just a couple of basically RAP forecast soundings. So RAP is a model, and these are just kind of proximity soundings next to known supercells that he's pulled together, so you can kind of understand the environments next to supercells. And you can see on the left, this case where you have a 3 to 6 kilometer lapse rate, which is typically when you're talking about mid-level lapse rates, if you ever heard that term, that's what it's really referring to. Somewhere really between 700 and 500 millibars. You can see on this left side, you notice how that red temperature line kind of goes mostly vertical and it doesn't go to the left as much. That's a pretty weak lapse rate, so it's about 6.8 Celsius per kilometer is what I calculated. And then on the right, Pilger. You all know Pilger. Some of y'all do. Pilger, Nebraska in 2014 had a lapse rate above 8, and the tornadoes were great that day. Violent tornadic supercell, and definitely the instability contributed to that, I believe. And you can see that layer highlighted a little bit better here. And again, shout out to Cameron for providing these soundings. All right, conditional instability. So the reason it's conditional is because of the cap. Unconditional instability would be like, auto convection, like, the temperature at your surface is always, as you go up in height, your parcel temperature is always greater than your environment. And that's almost never going to happen in the atmosphere. Conditional instability is pretty much the tickets here. So when we're talking about conditional instability, air is conditionally unstable if it will continue to rise above the level of free convection. So in the other session, we talked about that level of free convection is basically the point that is at the top level of the cap layer. So it's the point where your parcel temperature is greater than your environment, and there's basically nothing holding it back, and it just goes upward without being inhibited until it reaches the tropopause. So again, remembering that the change in environmental temperature is the lapse rate that we're talking about here. So parcel temperature would be, if you can think about it, that's the temperature of the updraft. So if you're thinking, that's the storm, the parcel temperature. So it's cooling at a lower rate than the environment around it. This is the clear air. The red line is the clear air around the storm. So that you can see why that hot air balloon would continue to rise. All right, and you can see that area between that, we've talked about that, that's CAPE. Convective available potential energy just gives you an idea of the magnitude of how much energy there is for updrafts. Okay, we just talked about that. That's the integration of the total positive instability in joules per kilogram. And to maximize that, we talked about this in the other session, but you need really three things. Steep lapse rates, we've talked about that just now. High surface temperatures, so you can increase your CAPE if you have higher temperatures, and then higher dew point temperatures. And as we talked about in the other session, it's actually remarkable how much more CAPE you can get just by tweaking your dew point up just a little bit. So looking for dew points is something to think about while you're out there chasing. Rules of thumb, and this is not anything scientific, but just my own personal experience, I'll just say that. Really, kind of early on in the chase season, you don't need a whole lot of CAPE because there tends to be a lot of shear out there. So I used to look for like about 1,000 kilograms in March. In April, maybe above 2,000 kilograms, and then after May, you'd say, okay, 2,500 is pretty good. So that's what you'd be looking for. And you think about extreme instability that time of year, 3,500, 4,000. El Reno, I believe, had 6,000 CAPE, which is just absolutely remarkable. And then, of course, the infamous Gerald, Texas tornado, right? The F5 from 1997. I want to say it had 7,000 CAPE. Just unbelievably high. It's very unusual to see a storm in that kind of environment. Usually it's capped or you get like a mesoscale convective system. So, I don't know. There's a little bit of a Goldilocks aspect of CAPE, You can't have too much of a good thing. All right. And then you have the convective inhibition, right? So that's the other side of the coin. That's that kind of middle layer between kind of the surface boundary layer moisture and the CAPE above that. It's the integration of that total negative instability. Some can be helpful. But too much is not good. So generally speaking, you want to have at least a little bit, because if you don't have enough of a cap, and that's what convective inhibition is, you've talked about the cap, that area of the warm layer right above the ground that kind of keeps the storms from developing, that does help that instability to develop, if you think of it, right? Because, those thermals go up, and if they go up immediately, right, they use that energy really quickly, and rather than letting it build up. But if that cap holds for longer, then that energy can build up. So you want a little bit, but maybe not a lot. And here's something that I would say is pretty important in my experience in storm chasing. I've been storm chasing over 20 years now, and I'd say one of the most important factors in choosing a target area is sunshine. And I think that's kind of obvious, but low-level lapse rates relate to that. So when I'm going chasing, I often am looking for areas where maybe the cirrus has broken up, you're starting to see some sun coming through, heating that ground. So maybe in the lowest 1, 2, 3 kilometers, you start getting pretty good lapse rates. That really helps with that low-level stretching. So we talked about spin and we talked about stretch. That's why that's so important. That's the ice skater bringing her arms in. That's what the low-level lapse rates represent. So you can definitely achieve that through strong TD. I listed that twice. But the best way to see this is on satellite. Cloud streets are going away. So, if you see cloud streets, you know what I'm talking about? They have those lines of cumulus, and it looks really stable. And that's what that represents, is when you see cloud streets, that's stable. But when they break up and they start bubbling up, that's when you know you're close to convective initiation. And I showed this, I think, to really illustrate something about chase targeting. This is June 12th, 2005. Most of you probably don't remember this one, but I do, because I was targeting the outflow boundary on the north side there, because, what do you do when you're chasing? You target the boundary intersection with the dry line, and that's what we did. But that was actually kind of closer up to here, and you'll notice that the clouds here, although a little bit bubbly, there was a lot of overcast there earlier in the day. And so what happened is that the temperature didn't warm well enough to where really the low-level lapse rates got very high. And it turned out that this development down there near Jayton, Texas, ended up being the area where the big tornadoes formed. So we missed it. And that was a big part of it, was the low-level lapse rate. So if you're looking for, all else being equal, you want to look for a place that has a little bit more heating. Okay. Now this is the physical part of this. So we've talked about like the thermodynamics of how it works on a Skew-T log P and kind of the rules of thumb. But how do you get that on a physical level? Well, it all starts with westerly downslope flow. And I'll illustrate this with a very crudely drawn picture of mountains. So this is what I would say is the Rocky Mountains. So up is that way, east. So you've got Albuquerque, Amarillo, Oklahoma City. I've shown where 850 millibars is, 500 millibars. And so what happens, let's say you have a westerly wind. It's going over the Rockies, okay? So it goes up the mountain, and then it has to come down the mountain, right? Well, it turns out that when you have air going down the mountain, you've been to the Rockies, right? Some of you. The air is less dense up there. And so once you start getting that air that's less dense and you start to compact it as you go down the mountain, right? It's following the terrain. As you go down the mountain, that air is getting closer and closer together. Those molecules start rubbing up on each other and getting pretty hot. And so that actually ends up with compressional warming. And so as the air goes down slope, that's a compressional effect, a warming effect. And if you've heard, I don't know if you've ever heard of it, but basically this same effect in meteorology is what leads to the so-called snow eaters in the Denver area. So sometimes you'll get a lot of snow, and then you'll get a westerly wind over the mountains, and then that snow will be gone in a day. That's because of this effect, downsloping, compressional warming. So there it is, cool at top, warm on the bottom, and then you start forming an elevated mixed layer. So what this means, and let me just orient you to this particular figure here. This is from some work by a guy named Roland Stoll, and this is basically just showing the evolution of the boundary layer during the day. So you can see here, you've got noon listed on the left, sunset, midnight, sunrise, and noon. So you can see the mixed layer. And what this means is basically the sun comes out, right, heats the ground, ground heats the air, And then the air near the surface is warmer than the air above it. So what happens? Warm air rises, right? So the warm air rises, the cool air sinks, and then you get this big churning effect known as mixing. And so that happens during the day. Incidentally, it also brings down a lot of energy, kinematic energy. So like the wind just off the surface starts to come down. So you've been in Oklahoma or West Texas or whatever, during the springtime, during the daytime, right? That it gets really windy. And the reason it gets really windy is it's taking that air that's moving really fast just off the ground and it's starting to mix it down to the surface. So that's that effect. So that's the mixed layer. Then at sunset, the heating stops, right? So you cool off the surface. Once you cool off the surface, then it inverts that process, no mixing. So then what happens to the momentum? The momentum goes back up into the atmosphere. And so that's why you talk about the low-level jet, right? Low-level jet happens usually around 7, 8 p.m. That's because of this effect. You stopped mixing, and now that energy that was kind of dispersed evenly through the atmosphere has actually kind of risen a little bit off the ground. And you know that happens to be actually pretty good for tornadoes too, because once you get pretty strong air moving off or pretty strong wind off the ground, not so strong beneath, you get that really big turning in the atmosphere. So that's why this time is so good for tornadoes. So let's talk about this a little bit more. Surface heating, as I mentioned, drives it. Heat and moisture move upward and downward. And this is something that I learned pretty recently from Rich Thompson. But if the height of the dry line circulation is higher than the moist layer, there's a good chance you'll initiate convection. So this is pretty handy when you're thinking about, okay, are we going to get convective initiation today? You can look at the height of the mixed layer west of the dry line to determine if that's higher than the moist layer to the east. So I'll demonstrate this in the picture. So, all right, this is April 14th, 2012. So probably some of you chased that. That was the big outbreak, high risk tornadoes, I think northern Oklahoma all the way up through Nebraska. This is the Lamont sounding from that night. And what you see here is the top of the moist layer is about 700 millibars. And if you look at the sounding at Amarillo, which would be a good, I guess, proxy for the height of the mixed layer or the height of the dry line circulation to the west of Lamont, because Lamont was in the moist area. If you look at that, it's 550 millibars. So the air is mixing all the way up to almost the middle level of the atmosphere. So if you can imagine, as that mixing is going eastward, it's churning up that moist air, bringing it to its level of free convection. And once it gets to that level of free convection, it just shoots off. So we got all these different thunderstorms up and down the dry line producing strong to probably even violent tornadoes. All right, so you have that mixing, you develop the elevated mixed layer, as the name suggests, and then let's see what happens next. Formation of the lee trough. So this is kind of interesting. So we talked about this air being pretty warm down here, this air above it being pretty cool. Let's think about this. So if the air is warm at the surface and the air above it is cool, what's going to happen to that air? Rises. Rises right there. And so what happens there is that, there's no vacuums in the atmosphere. So what goes up, you have to fill that in with air coming from the other side too. So you have air moving down westerly, and you have air coming in from the east, from the plains. Oh, and by the way, I did make a note that this process can take days. So, we're talking 3-4 days in advance of the storm system that you're interested in. This process can be happening with that westerly flow. So, this is something like if you've got a severe weather event coming up in 4 or 5 days, you can start seeing that westerly flow over the Rockies. You're saying, oh yeah, the elevated mixed layer, that's getting going. Going to be some potential for instability there. And then, of course, we get this low in the lee of the Rocky Mountains. That's why they call it the lee trough. So the east side of the Rocky Mountains, that's what that is. So I wanted to show you this process prior to the big, more, I guess that would be Roselle, Shawnee events. You remember that? May 18th through 20th, 2013? This is how that elevated mixed layer came to be. And so remember, we're looking for strong westerly flow over the mountain. So the mountains are right here, obviously. And then you've got pretty westerly flow, 20 knots from the west-southwest there in Denver, a little stronger further north, but generally pretty weak. So you wouldn't expect to see much in the way of a surface response. Indeed, really, there's no areas where the pressure is less than 1,004 millibars. That's what I use to kind of show where the lee troughing is occurring. Okay, so you go May 18th, 2013 at 0Z, so that'd be the 17th at 7 p.m., 500 millibars. You see a little bit more flow, but not particularly strong, but you do see this nice 30 knot there at Amarillo, due west. So the component of the wind that is from the west also matters. So you want as much westerly flow as you can have, as well as some speed to it. So you'd expect to see a little bit more troughing. And indeed, if you kind of analyze what was going on there, you can see in the red, that's areas where the pressure starts to lower, so you're starting to see the development of that leaf trough. And so what that's going to be doing is, by the way, spoiler alert, this is going to create kind of almost like a sink where, basically all the air rushes into this trough. If you're west of the trough, it's going to rush in from the west. If you're east of the trough, it's going to be from the south and the east. And of course, you guys know what south and east? The Gulf of Mexico, right? And that's where all that moisture is locked up. And actually, you can see there's pretty good moisture already. So it's part the pump is already primed. Kansas is the first place where all this stuff happened. Roselle, EF4 happened the next day, a day after this. Dew points in the low 60s, pretty good. Not great for late May. So we need some work on that. So the next morning, you see that the flow has increased just a little bit, kind of broad-based, but it's kind of backed a little bit to the southeast, so there's not as much of a westerly component. So you might expect that because we've backed to the south-southwest rather than just pure westerly flow, that maybe you wouldn't get as much of the lee troughing effect. And indeed, that's what we saw in the surface map. So you didn't see as much of the pressure effect of compressional warming. But by the time of the Roselle event, 7 p.m. on the 18th, you actually do see really significant component of westerly flow. Looks like we've had some sort of shortwave trough going through western Kansas, and even more energy, obviously, coming back in over the Four Corners region. And indeed, that's where we really start to see the pressure lower. In fact, got much lower than 1,004, and that's when essentially the moisture advection machine really got kicked in high gear. So this ended up bringing in the moisture. You can see 850 millibars. This is the low-level jet from that night. You can see how, if you're lowering the pressure right here, right, all else being equal, if you're lowering the pressure right here, if you were you were here for the introductory course, you'll remember that the speed of the wind is proportional to how close together those iso heights are, right? Or isobars in this case. Actually, it would be iso heights. And so since those are really, really close together, these heights are lowering, these are staying the same, so that wind increases right through there. And it's from the south and southwest, so it's bringing up those high water vapor mixing ratios up into Oklahoma, into Kansas. And you can see there, that's the low-level jet. And it is literally carrying or advecting the moisture. And that's what happened. This is just an unbelievable event that happened over the course of that day, or those few days. I saw the Roselle tornado that night of the last image there, and then Shawnee was the next day, and more, the EF5 was the day subsequent to that. So it was just an incredible time, but it shows you really how compressional warming works. All right, now the next ingredient is moisture. So one of the things that really you have to look for when you're talking about predicting tornadoes is moisture depth. So, you may see, say, a surface map, and it'll show like, a 72-degree dew point. That's fantastic. But if that moisture is only skin deep, like I say, it's only 10 or 50 meters deep, it's just essentially stuck in that very near surface layer, then once that mixing begins, right, throughout the day, those thermals start happening, it mixes out that moisture, and so then you're left with nothing. So deep moisture prevents the turbulent mixing, and it keeps instability high and mitigates downdraft strength. So kind of tying that back to what we were talking about at the very beginning, remember, tornadoes require two things, spin and stretch. So if you can mitigate downdraft strength, right, that's going to allow your stretch to be strong, right? That's what moisture is all about. That's why you want low LCLs, is because they help you to keep your stretch. And this, again, moisture depth, the rule of thumb for this is about 75 millibars depth is what you need for tornadoes. This is a nice proximity sounding from 2004. Probably most of you won't remember this one, but I remember this one because it was such a dynamite event in central Illinois, a little town called Roanoke. I don't know how many of you remember that tornado. Roanoke, Illinois, 2004, got hit by a tornado, and you can actually see that the moisture depth isn't, particularly strong, and maybe you got 75 millibars of good moisture there. It's kind of at the bottom end, and it kind of falls off after that. Now, this is a forecast sounding, so that, I don't know how much you can trust that, but this is the tornado that happened from that, so it was definitely enough for that. So, but that's kind of about the minimum that you'd be looking for. It's about 75 millibars. And source region for moisture. This is another one. We talked about, how development of steep lapse rates takes a lot of time, 3-4 days. It takes a lot of time to transport moisture. So when you're talking about severe weather ingredients coming together, you can actually see these things coming together multiple days in advance of approaching troughs. And for what it's worth, and I'll just say this a little off script, sometimes it's good, like if you're wanting tornadoes, I guess that would be this crowd, to have a sacrificial, as it were, shortwave trough move through. So sometimes you see a really good trough move through, and it's like, it's going to produce big wedges, and then you don't end up having enough moisture. But it primes the pump, right? So there wasn't enough moisture for that event, but then there's another shortwave trough on the heels of that, right? And it comes in, and all of a sudden you have 65, 70 degree dew points, and it's like, okay, that'll work. And so that's something also to keep in mind. But early in the season, it's really important, I think, to think about identifying moisture source regions. Even if you have southerly flow over the Gulf, you might not actually get quality moisture, and I'll show an example of that. But later in the season, this is less important. So if you get to like May, June, 70 degree dew points are ubiquitous. So it's not really that important to think about this, but particularly early season. So this was an event, prior to an event, I should say, in March of 2004. And I just really wanted to show you kind of the pattern that developed over the Gulf of Mexico in terms of the surface flow and how that affected moisture transport. So again, another slow process. It takes days. This was, by the way, the severe weather event that I'm talking about happened, I believe, on March 27th. So this is March 24th at 0Z, or March 23rd. So this is 4 days before the big event. And what you see here, I wanted to point out over the Gulf, this type of flow. So you see you have northeast flow over the eastern Gulf that is taking pretty low dew points. If you look at that, 47, 51, and transporting it around the northern Gulf and into the plains. So that's not really that great moisture, even though you might be thinking, if you're in Oklahoma, I've got a southerly wind, we're going to get some good stuff from the Gulf of Mexico. But the source region itself doesn't have very high dew points. And you see this going through time, and it gets a little bit more southerly, but notice that the real deep juice is just not there. It doesn't start really appearing until right before the event, I believe. You can see, okay, yeah, you start to see 65, 66 dew point. Okay, that's better. But this is the time of the event. You can actually see, this is what is, I think, a supercell just west of Oklahoma City. I saw a tornado, actually a couple tornadoes with that particular cell, but it was pretty weak. And I believe large part of that was because of, even though the shear profile was fantastic that day, we just didn't have quite enough moisture. And then one of the things I wanted to talk about is the effects of inland mixing. So this is something to also contend with when you're talking about moisture, particularly early season. So a little bit of crude analysis here showing the 65-degree isodrosotherm, which is the line of constant dew point. And, it's there in central Texas. Time of this is about a day and a half before the event I was just talking about. So it's like, okay, we've got a 65-degree dew point. That's right there off the coast of the Gulf. Southerly winds, this ought to be good. But then notice, literally a day later, 24 hours later, did you see that move at all? I don't think I did. It was literally stuck in the same spot that it was 24 hours before. And the reason for that is basically this mixing thing that we were talking about. We can look at that through these soundings. So this is Corpus Christi. The time of that was 12Z, so that would have been 7 a.m. or maybe 6, depending on the daylight saving time. They're right along the coast, pretty good moist layer. I mean, that's, at least 100, 150 millibars deep, good moisture. So there it is. And then you go to Dallas, or you go to Fort Worth to the north, pretty decent moist layer, but it's a lot, I think I highlighted it, it's a little bit lower moisture in terms of like the actual dew point's a lot lower. Also, it's a little bit less deep. And one thing I'd really point out is notice how that air is pretty dry right off the deck. And so what's happening is that moisture is coming in to Texas and it's moving north, but as soon as it counters that dry air in Fort Worth, in that kind of area, that mixing is just mixing out that moisture. And you can really see, the effect there. So the moist layer has deepened. It's gotten a lot deeper, which is great, but the actual value, the magnitude of the moisture is a lot lower than what you'd want. And that's the reason for that is that the mixing has, unfortunately taken out essentially the moisture for that. Okay. So some offsetting factors for mixing. So, it's not all bad if you have dry air inland. I mean, obviously the air tends to be more dry over land. Moisture movement by the wind, advection, can neutralize inland mixing. So if you have a really strong low-level jet, that's something to keep in mind. Sometimes it just, quickly moves very high water vapor mixing ratio air to the north. Real memorable event, and actually this part of the world was the Red River outbreak, I guess Terrible Tuesday in 1979. That was a really good example of how that moisture advection kind of offset some of those inland effects. I mean, you had a very, very strong low-level jet. That was the Wichita Falls F4, and it was, I believe, a just-in-time moisture situation. Tim can validate that for me, but a strong cap, by the way, can also prevent out the mixing. So sometimes you'd say, oh, I don't want that strong cap, but the strong cap can prevent the mixing that would decrease the quality of your moisture. So sometimes that can be helpful. Now moving on to vertical wind shear. Vertical shear is what organizes storms. So, you can have instability all day long, but if you don't have any shear, it doesn't help you. And so, I mean, this is one I've used before. This is just shows essentially linear shear, which, we're not talking any changes in direction, but just simply the old paddle wheel experiment, right? You put the paddle wheel in the middle of the atmosphere. You've got winds moving really strong. At the top of the atmosphere, down low, it's moving not as fast. Spins in between. Okay, you've got instability, so you throw in an updraft, and lo and behold, you actually get rotation in the vertical. So that's what takes that rotation in the horizontal, tilts it into the vertical, and you have these counter-rotating vortices. So that would be what you call your straight Hodograph kind of situation. So essentially, neither the left mover or the right mover would be favored. So this would be the right mover. This would be the left mover. And in that situation, you'd have to see how that played out to see which one would actually end up becoming dominant. But essentially, propagation through rotation would cause both of these storms to kind of split off and move in different directions. Let's see. Now, if you actually did something a little bit different, right? You had maybe instead of a due westerly wind in the case that we had before, but you kind of threw in, say, a southwest wind at the surface, so there's a little bit more turning with height, right? We're talking about a clockwise turning Hodograph. That's going to be a different situation. What happens, we'll talk about this a little bit more about streamwise and crosswise vorticity, but basically, your storm is ingesting like spin into it. Instead of just kind of waiting to ingest it, it literally from the jump takes it in. And it turns out in this kind of configuration, the southern storm ends up being the most impressive, and you can see how, the rain rotating around that southern circulation ends up producing that pretty well-known radar signature. All right, so bulk shear, that's used to approximate the shear through the depth of the storm. 0 to 6 kilometers is a standard layer. You're going to look at 0 to 8. Something that I think is probably wise to do, to be honest, is effective shear. I didn't really want to get into talking about effective shear, but basically it takes into account your thermodynamics as well, because really what shear you're interested in is the cloud-bearing layer, right? Not just some random layer. Sometimes you have elevated supercells, if you've ever heard of them. Basically, instead of having a supercell that takes in air directly at the surface and transports it upward, that inflow layer is actually a bit off the ground. And those elevated supercells tend to be, I lost my train of thought there, but they tend to be hailers. They tend to be the ones that produce the big hail. So it'd be good to use effective shear for that. 30 knots is probably a good rule of thumb for knowing what the minimum level of effective shear is for a supercell or storm organization. My understanding of bulk shear is kind of evolving a little bit as I've kind of looked at Cameron Nixon stuff, to be completely honest. I think right here what you're really looking for with bulk shear is you're looking for storm longevity more than supercells. When you're talking about supercells, you're really more interested in storm relative felicity, which we'll get into. But what you really don't want is you don't want rain kind of interrupting your inflow layer. So you're talking about a rainy forward flank, you're not getting that inflow into the tornado or to the circulation. That's not a good situation. So we'll get into that here in a second. But one of the things I wanted to talk about here is the importance of mid-level rotation. And this is an example from 2008, the Jewel, Kansas, I believe it was F3 tornado. I chased this with Karen in the Dows that day. But this was producing, I believe it was at least a 3/4 mile wide wedge at this time. And it turned out that if you looked at kind of like the convective inhibition on SBC's mesoanalysis archive, it ended up being, I think it was more than 100 joules per kilogram, may have been much higher, I don't even know. It was off. You couldn't really tell how strong that cap was, but the point being, the cap was really strong, but yet you were still producing wedges. Why? Well, it turns out that thermodynamics is only part of the equation. You also need rotation, and that's really, in this case, because we had developed that supercell much further to the west, the rotation was able to take over, and it was literally just creating this almost like a vacuum cleaner to where it was like, I don't care about the cap, I'm just going to keep going. And you'll see that from time to time. So really what you need first is a supercell, and then if it moves into a capping layer, okay, that may not be so bad. Now, the weakness of bulk shear is it only measures the magnitude of shear, so just basically, a brute difference between winds in a different layer, in a layer, and it does not consider the direction of the shear. So we really need to dig into the hodograph to understand more about this. And with the hodograph, you really have to think in terms of relative motion. So relative motion is, just a classic example of you drive like me or maybe somebody who you dislike on the road who drives really slow. That would probably be me and then somebody else passing you, or you might be passing them. So if this were me, I would be relative to them moving basically 20 miles per hour in reverse, right? That's relative motion. They, relative to me, would be moving at 20 miles per hour. So that's what I mean by relative motion. So we talked about the hodograph in the first session. Now we want to talk about the storm relative wind. So again, storm relative motion, this is what the storm itself experiences. So we're mostly interested in that right mover, right? We're not interested in the left, we're interested in the right. So we're going to take the right mover as our origin for our vector, and we're going to draw a vector to the hodograph. You'll see that here in a second. There it goes. So that's the storm relative wind at the surface. So it's basically, that storm is essentially experiencing a southeast wind. And at 1 kilometer, it's like a really strong southerly and so forth as you go up into the atmosphere. That's what storm relative wind means, what the storm is actually experiencing. So that's what we care about. Now, the area bounded by the hodograph and the storm relative winds at the top and bottom of the layer, that's actually the storm relative felicity. So, for example, here's the 0 to 3 kilometer storm relative felicity. That's basically the bounding that you'd get in that layer. And 0 to 1, you can see what that looks like there. So, I typically use 0 to 1 kilometer SRH. Studies have shown that like really your most important layer is pretty close to the ground. Some people think it might even be closer to the ground, maybe like 500 meters is what you're really looking for in terms of low-level shear. And this would be, again, for tornado potential, you might consider these rules of thumb. I like to look for at least 100 meters squared per second squared for tornadoes, 200 for strong tornadoes, and 300 for violent. I would commend you to look at some real research other than my rules of thumb, but I think, this might be good enough for some of you. Now, streamwise vorticity and storm structure. Now, this is something I've kind of dug into a little bit, like I said, talking to Cameron Nixon a little bit and watching a lot of his stuff, great stuff. And so I'm not the expert on this, I'm just learning. So I'd commend you to look at some of his stuff. But we can dig into, this is some of my stuff first, and then we'll dig into his. So vorticity vectors, I forgot about this part. So vorticity vectors, so we've got the shear, right? These are the winds higher up, winds down low. And then the wind the rotation, the spin in between is in that orientation. And that the orange vector there, that's the vorticity vector. That's what we're talking about when we talk about the vorticity vector. And you can really use the right-hand rule for that. Some people who've done meteorology know what I'm talking about, or maybe calculus. The right-hand rule is, basically hold up your right hand. Your fingers go in the direction of the vector you're interested in. What your thumb coming out is the resultant vector. In this case, that's the vorticity vector. So your shear vector is what you put your fingers on, and then the vorticity off to the left. So when you put that on a hodograph, here's how it'll look. And by the way, the vorticity vector is, the length of it is proportional to the shear magnitude. So basically, that shear vector on the hodograph, if that's a longer shear vector, then your vorticity is also going to be correspondingly large. So there's a vorticity vector there off to the left, right-hand rule, off to left, off to left, off to left. Okay, now we're ready to talk about streamwise vorticity. So streamwise vorticity is basically how much of that vorticity vector does the storm actually experience. And so the way you can tell that is by plotting your storm relative wind relative to your vorticity vectors. So in this case, from your right mover, your storm relative wind goes back to the surface to 1 kilometer shear vector, and you can see that vorticity vector is pointing this way. Notice that the storm relative wind is also pointing the same direction, right? Basically, the wind that the storm is experiencing is in the same direction that the vorticity is spinning. So basically, that updraft is, for the storm is experiencing pure vorticity. Here, it's not quite as parallel, right? There's a little bit of an angle there. Here, it's much more of an angle. But generally speaking, that's a pretty good hodograph for streamwise vorticity. That's what they call it, when that storm relative wind and the vorticity vector kind of align in that same general direction. Okay, so kind of a way to summarize that so you can see it a little bit more clearly. The shear vector that way, vorticity vector that way. If your storm relative wind is pointing in the same direction, that's streamwise. If it's pointing orthogonal to that, that's known as crosswise vorticity. By the way, you're never going to get pure streamwise or pure clockwise in the atmosphere, almost never. Sometimes you can get some good exceptions, but most of the time it's going to be some version of streamwise and crosswise. This would be an example of a very streamwise hodograph from reality. So this is the Pilgrim, Nebraska violent tornadic supercell. You can see it's very streamwise in the lowest kilometer. Notice that I believe this is the 3 kilometer felicity is 319 meters squared per second squared, pretty good. And so you can see how if you were to draw a vorticity vector, it would go this way, and then the storm relative wind points in the same direction as the vorticity vectors. So that's good for tornadoes. It means your storms are ingesting perfectly good spin. We want spin and we want stretching. That's what happened. Photo by Ethan Schisler. And then streamwise here in the lowest 500 meters. So, I mean, this is not bad. I mean, if you're going to see streamwise vorticity, you want it to be in that. All right. So, in this case, it's actually pretty good in that lowest 500 meters to maybe not quite a 1 kilometer. We'll just call it 500. But notice that it's not so streamwise at 3 kilometers. If you think of where your vorticity vector is, say, between 2 and 4 kilometers, it's almost perfectly crosswise to the storm relative wind there. So turns out that doesn't matter that much in the middle levels. Really, the shear you're looking for, again, is in that lowest 1 kilometer, maybe 500 meters. And this is the tornado that I observed with that particular hodograph. This was out there, gosh, I had the name of the town there, but out there maybe in McLean, Texas, Howardwick kind of area. Very pretty tornado. This was the stuff I was talking about with Cameron, okay? So storm structure and hodograph shape. I'm just going to try to loosely summarize what I've learned. So there are 2 concepts that I'm going to focus on, and that's the low-level storm relative wind versus storm size. Turns out there's a relationship there. Makes sense when you kind of think about it, but I didn't know about it until recently. And the upper-level storm relative wind and your precip pattern. And so I'm just going to be focusing on just the lowest kilometer in this particular set. So you see your right movers maybe going northeast at, say, 30 knots, 35 maybe. And your surface to 1 kilometer vector is right there. You notice that your storm relative winds compared to that is pretty weak. I mean, they're pretty much right next to each other. So that's the point. The storm relative wind vector is very small. That turns out, if you see that pattern in the inflow layer, and you otherwise have a hodograph that supports supercell, that leads to mini supercells, low-top supercells. So it doesn't mean there won't be tornadoes. It might mean, though, that they might be small. Interesting. The opposite is true, right? You get that big storm relative wind in the lowest levels. Turns out you get large supercells. And that makes sense intuitively, right? Because if you think about it, the lowest level of the storm is where you get that energy, right, going into your thunderstorm. And if you have just a little bit of wind, it only gives it a little bit of energy. And if you have a big wind, it gives you a lot more, right? So you get a bit more expansive, maybe your motherships. That's what Cameron's research has revealed. Also, when you're talking about the other end of the spectrum, right, you're not talking about the low levels, you're talking about the upper levels, talking about outflow. Weak storm relative wind in the highest levels leads to high precipitation supercells. That may not prevent you from seeing a tornado, but it may mean you have a hard time getting in there and seeing it. And then in this case, you have your right mover pretty close to your upper level shear vectors there. And so your storm relative winds are very short. So you might expect to see an HP supercell in this kind of situation. And of course, the opposite is true. If you have pretty big wind separating, your storm motion from the upper levels of your hodograph, it turns out you get low precipitation supercells. So that's something to keep in mind. Outflow boundaries, pretty important. Great sources for enhanced low-level shear. Generally form from previous night's convection. So you really do need outflow boundaries for them to work for tornadoes. You really need them to bake a little bit. Talk about the low-level abstrates. It's pretty important. And this is what that would look like. So you have like the cool outflow maybe to the north, and then the warmer area to the south. And then you'd see that kind of rotor developing. Really, you need your outflow boundary to stop moving. If it's moving to the south, that's probably a problem. What you need is at least neutral and preferably moving to the north. This is one that worked pretty well for a few of us here. This is May 24th, 2016. This is one of my best chase days ever. Dodge City, Kansas. You can see this outflow boundary hanging out kind of from Colorado, Kansas, up into Missouri, 7 in the morning. And you can look at 1:45 p.m. We talked about low-level abstrates. We talked about the baking, getting that that mixing occurring. You want that to help you warm that boundary a little bit, because on the cool side of the boundary, it may be a little bit too stable. That's what happened. There wasn't really much preventing sunlight, and so that outflow boundary ended up taking the shape of kind of the inflow to the, or the inflow, but the return flow to the lee trough, and you ended up getting this beautiful surface pattern that you like to see as a storm chaser, southeasterly winds with upper 60s, low 70s dew points, and of course, obviously, a big tornado outbreak ensued. And then lift, kind of running out of time here, but basically with lift, there are three types of lift. You have large-scale lift, which I'll talk about. You have mesoscale lift, and then you have storm-scale lift. I would say the mesoscale lift may be a little bit more important when you're considering where storms may form, and that's because you'll notice I've put in the parentheses the speeds at which that would entail. So 10 centimeters per second for large-scale lift. That's going to take a long time to get through the troposphere if you're only moving 10 centimeters per second. Whereas if you're moving 10 meters per second, that goes pretty fast. So, definitely more effective to be talking about mesoscale lift. Large-scale ascent. So we talked about the Coriolis force in the beginning, balances the pressure gradient force. I won't get too much into this. We're kind of losing some time here, but bottom line here is there are really two factors you're going to look for at the upper levels to determine if there's going to be upper lift. So change in vorticity advection with height is one of the things that if you see that basically vorticity that's being moved by the wind, typically downstream of that vorticity you get some lift. And then if you get warm air advection, that's the second piece. Any warm air advection is also going to cause some lift as well. So the way to think of this, basically differential positive vorticity advection is a mouthful, but basically meaning if your vorticity is higher above than it is below, it's being moved by the wind, you're going to get some rising motion out ahead of that vorticity. So you can see that here, basically you can infer a little bit of vorticity right there. This is April 27, 2011, by the way, the big super outbreak. You can see, you get that big ball of vorticity right there in south central Oklahoma, and the wind is carrying that towards Arkansas, and so you'd expect that's where the lift would be. So that's one way to look at it, so there'd be some lift from that particular feature. If you're looking at, say, satellite, drying is a good sign that you have some lift going on somewhere ahead of that. So anytime you see an intersection between like that orange color and kind of the brighter colors there, that would be an area where there's a vorticity maximum, and you would expect to see some lift out ahead of it. Warm air advection, basically anytime you have temperature advection, you're going to have some lift, and so forth. And so, by the way, this profile that's nice for supercells, the veering wind profile, where you go from southerly to westerly flow, that's warm air advection, just by definition. So anytime you see that, there's rising motion. So that's an easy one. And I won't get too much into this, but basically this is curvature divergence. So basically, due to curvature and some geostrophic differences here, you actually see divergence downstream of troughs. It just explains why you get convection out ahead of troughs. It turns out that this factor is actually more important than the straight jet theory, which we'll talk about here in a second. But basically, and I'm losing time here, but left front quadrant of the straight jet is probably where you're going to be looking for your lift. And then also the right entrance region. Although I will say that right front quad is also a place that you can get tornadoes as well, particularly because of that ageostrophic divergence effect as well. So with that, I think I probably better wrap it up. I left a little bit on the table there. So if you have any questions that you want to pose, feel free to come up after, and I'll be happy to answer any questions you may have.
Thank you so much. I'm nervously watching the radar, too, because I'm actually supposed to be on the air tonight. I've got backup, but I know you guys would like a little excitement. I'd kind of like these storms to behave a little bit. But my name is Dan Henry. I'm the chief meteorologist at Fox 4 in Dallas. I think you guys have had your fill of meteorology today, some great stuff. I'm going to take a little different approach here. Eric wanted me to talk about safety because we know how important that is. And I'm going to also put a little different twist on it, tell you a few stories as well. But let me, first of all, for those of you that aren't from Texas, a big welcome to Fort Worth. Welcome to North Texas. I know we've had people coming here from literally all over the country. I think I saw somebody on Facebook today from New Zealand. So wherever you are, welcome to North Texas. I've been with Fox 4 now for 21 years. I've been doing broadcast meteorology now for 34 years. And I wasn't a natural at all. In fact, I was petrified to get in front of people and talk, which is a big problem when you want to be on TV. In fact, I was so nervous speaking in front of people, I made people watching me on TV nervous. That's how bad it was. But I overcame that fear, and I love what I do. But I also appreciate so much what you guys do. I can't say that enough. Because what I do on TV is, and it's our primary responsibility, is keeping people safe. In times of severe weather, we tell them about, the dangerous storms that are approaching. I can only do so much, though. It's one thing for me to show a radar image on TV. As impressive as it may be to you and me, it really doesn't mean a whole lot to the average viewer at home until they see video, until they see live streams, until they see photos, until they hear reports. When I share that with people on the air, that hits home. That is where my message really starts to be amplified tenfold. And so we have our dedicated group of chasers that have done amazing work for us, but just a big thank you to all you guys out there for what you do, because what you are doing is helping to save lives. That is helping to save lives. And before I get into my little spiel here about safety, I want to take some time too to talk a little bit about risk. And what I didn't have enough time to really come up with a topic or a name for my talk tonight, but if there's a theme, it's calculated risk. Someone want to help me out with how to forward this? Which one am I supposed to be pushing here? There we go. Okay. So we all know that storm chasing is risky. It's inherently, there's a danger there. We all know that. By definition, a risk is anything that involves uncertainty or potential danger. They are often unpredictable, and the consequences, whether positive or negative, can range from minimal to severe. Calculated risks, that's a subcategory. That includes a higher level of preparation, analysis, or decision-making meant to minimize negative outcomes and maximize positive ones. And that's what I hope to at least partially accomplish here tonight, is have you operating from that subcategory, calculated risks, especially those of you that might be new to storm chasing, so that at the beginning of the day, you're preparing, you're analyzing the data, you're looking at the weather data. So that makes it more, you're going to be more prone to making better decisions to minimize those negative outcomes and to maximize the positive ones. Oh, let's go the other way. All right, got to tell you a little story here. This goes back over 20 years ago. I was working in Washington, D.C. at the ABC station there, WJLA. It's my very first time a storm chaser literally gave me a huge assist. Now, in Washington, D.C., back around 2000, we didn't have storm chasers. Heck, we didn't even have internet in my TV station. We had very little, surprisingly. The day before this big severe weather day, my co-anchor, beloved co-anchor, his name was Dale Solly, was out jogging and collapsed, died of a heart attack, early 50s, the day before this happened. Came into work the next day, and it's a skeleton crew to begin with on the weekends. We are all just devastated, shell-shocked. And yet, I knew I had a big weather day ahead of me. It was just me. That's it. Get in there. We had a couple supercells that were going across the Virginia countryside. doing some damage, some wind damage, some hail damage, a few small tornadoes, nothing major, until that supercell reached the Potomac River. It's late in the afternoon, and that river breeze increased the low-level winds, ramped up the low-level shear, and that thing lit up like a Christmas tree. In my radar, literally, there were shear markers all over the place. Now we're approaching 7 o'clock, and it's Jeopardy time. So those of you that aren't familiar, some of the most fire-breathing, venom-spewing emails and phone calls, even threats on my life, have occurred when I dare to interrupt television programming for a tornado warning. I had a conversation with a woman a while back who was just, she wanted my head on a platter because I had interrupted Judge Judy. And I said, ma'am, let me get this straight. I said, so you're telling me that until that tornado literally blows you off your couch, out of your living room, you don't want to hear from me? That's right. So there are people out there that are very, very selfish. But unfortunately, I don't have the capability of interrupting for just certain places. If we interrupt for some, we interrupt for everyone. So on this particular day, 7 o'clock rolls around, that storm is lighting up like a Christmas tree. The first tornado warning comes out. I go on the air. Stay on the air for about 2-3 minutes. Try to keep it short. Get the message out there. At this point, there's no confirmed tornado. Radar indicated. I get off the air. Phone rings immediately. It's my news director. Dan, what are you doing? You're interrupting Jeopardy. It's one of our biggest programs of the week. It's Sunday night. I really don't want you on the air. I said, Steve, I got a really bad feeling about this storm. A couple minutes goes by. This thing is just, it is looking intense. I go back on the air, do another short cut in, get off the air. Phone rings again. This time my news director's pretty mad. Dan, I told you I don't want you interrupting the show unless you know 100%. I said, Steve, you know what's going on around here. You know what happened yesterday. So I'm trying to, nobody in the newsroom wants to be here. Heck, I don't even want to be here. So I understand, but, you know, we're coming up now on Final Jeopardy. You got to, literally. I put the phone down. Phone rings again. This time, it's one of our engineers who happens to be a storm chaser and a ham radio operator. And he says, and he's out of breath. He's like, Dan, what the heck is going on? I mean, calm down, Dave. Tell me what's going on. You probably know more than I do right now. So all I can tell you is that I've been monitoring the hams. We got a tornado down here. We've got reports of damage. They're calling for any type of help they can get. I hang up the phone. I pick up the phone, call Master Control. The Master Control operator has to get me on the air. And I said, look, you got to get me on the air. I just got confirmation. He says, Dan, I can't do that. I said, what do you mean? I said, Steve called me. He doesn't want you on the air until after I was like, get me on the air. I said, I know the situation you're in right now. I'll take full credit here. Full responsibility on me. Get me on the air. He puts me on the air. I stay on the air for probably the next 25 or 30 minutes. As it turns out, this was the strongest tornado in Maryland history. Still, I believe to this day, Tim Marshall surveyed this. It was pretty much a continuous 70-mile track, 3 fatalities. That's the view from an aircraft. That's actually a picture in the other weather book I wrote, Washington Weather. That's a picture of the tornado over the Chesapeake Bay with a satellite tornadic waterspout. The next day, Tony Kornheiser, who many of you might know from Pardon the Interruption on ESPN, he was also on Monday Night Football for a few years, did front page article in the Washington Post ripping apart our competition. The NBC station stayed with the NBA playoffs, didn't do anything. The Fox station, nowhere to be found. We broke into coverage, and the reason I had the confidence to disobey direct orders from my news director and to do that was because of that one phone call. That one phone call from my storm chaser telling me what the heck was going on out there. So I can't tell you guys, there are times when we don't know. It may look really impressive on radar, but we don't know if there's a tornado or not. And so your reports are critical to us. It gives us that ground truth that we need to do what we do best on the air, and that's to warn people that are potentially in the path of it. Got to give a shout out to our Fox 4 Storm Chasers. A few of them are here tonight. Paul, Michael, Justin, Gene, Chad, Victor, Russ, Nick Busby. I know Nick and Michael are both here tonight. Russ was out getting that tornado that we're all being insanely jealous about out in Haskell County. That's Russ, though. See, I get kind of jealous all the time of all you guys because I'm always in the Weather Center watching it from a really far distance, and so I don't get to chase much at all. So anyways, I owe all those gentlemen a debt of gratitude. All right. I am not here tonight to throw anybody under the bus. In fact, I would say everybody in this room tonight, I don't care how experienced you are, I don't care how smart you are, I don't care how many degrees you are. There has come a point in time, and there will continue to come points in time, where you have been humbled to your knees by Mother Nature. Mother Nature has thrown you a curveball that you did not expect. Whether it's deviant storm motion or a tornado that literally you did not expect to develop that quickly, it happens. Okay? This was a very close call back in 2022. I think many of you probably know the situation here. They were actually driving back to their hotel at night. Storm was to their south. That storm took an abrupt north turn, and they got sideswiped by that tornado. Fortunately, no significant injuries, some bumps and bruises, but everyone okay. Very, very sad case here. 2022. I think everybody knows about this. These guys, 3 OU students killed after a day of storm chasing on their way back. There are dangers out there before you get to the storm. There are dangers that lurk out there while you're chasing the storm. There's danger until you literally pull into the driveway of your home and walk in the front door. You're not safe until you get home. And that is the goal that should be top of your mind before every single chase that you go on. I'm coming home tonight, safe and sound. That's what I'm doing. All right, I asked my chasers for some input here, some lessons learned. Here's what they shared with me. Be prepared and expect the unexpected. I think we all know that that's the beauty of what we do too. You never know what you're going to be getting yourself into that particular day. Every single chase day, every single storm is different. Don't let your guard down. Driving back into town after the tornado had passed, minimal damage except for a partially down power line. That line snagged my mirror, veered me into a ditch where I got stuck for hours as 6 inches of additional rain fell. Flooded roads left me stranded even after a farmer pulled me out with his truck. That's a long day. It's a long day. I think all of us have probably been in that position at one point in time or another. Some other lessons learned. Learn storm structure, especially young folks that are chasing, maybe inexperienced. Know what that storm is doing without relying on radar. You should be able to look at that storm and pick out and identify storm features that tell you what it's doing without looking on your phone, because you know what? You might not have cell service, which means you probably don't have radar unless you've got satellite-derived radar. No surprise here, GPS is not always reliable. And a farm-to-market road may look like that after 3 or 4 inches of rain. And then you're stuck. Let's talk a little bit about this. I think we all know what an SPC outlook like this is going to bring out the circus. I mean, you're going to have families in their minivans. Come on, kids. And, people that have absolutely no business being out there chasing storms are going to be right out there with you, on your tail, following you. Look, he's a chaser. He knows where he's going. And so you can see, that's obviously, we all know what that is. Look at the train going right up 287, cluster there in Oklahoma. That's just a mess. My only advice here is, a couple things is maybe avoid days like that if you can. You don't always have to follow the herd either. Clogged roads can create nightmare situations. Also, when you have a high-risk day, we all know, the atmosphere is primed, which probably means that you're only going to have a few hours maybe of discrete storm mode, and then you get this giant HP mess. And then the chase is pretty much over with because nobody wants to be out chasing that. So my advice might be maybe consider playing the lower risk area. Maybe go down towards the enhanced or the slight risk area where you're going to get maybe some more clear air to work with, fewer people to contend with, less clogged roads. And that might be a situation where you might be able to take advantage because instead of having 1,000 people on the same storm, maybe it's just you and 3 other people. That's Martin Cooper, the father of the cell phone. Never rely on one form of radar data. Wireless data and apps can be severely limited. I think we all know that with overloaded demand. Another satellite-based radar. Boy, if you can have that. Here's another thing, too. If you're chasing with a couple other people, and this shouldn't be the only determining factor, but maybe one of you should be on T-Mobile, maybe one on Verizon, maybe one on AT&T, because now you got 3 shots out there to have cell service instead of just one. I'm a child of the 70s, so there's going to be a couple of old TV references here. By the way, I would love to see a storm chase vehicle like this. That would be spectacular to see a Gran Torino out there. For those of you younger people, that is Starsky and Hutch, 70s crime drama, pretty good show. But have a chase partner. Don't go solo, especially if you don't have a lot of experience. You need another set of eyes and ears, trained set of eyes. Not your boyfriend or girlfriend that doesn't really know a lot about the weather, but a trained set of eyes with you in the vehicle to go chasing. If not one, maybe even 2. It's always not a good idea to go solo out there. Another reference to an older movie. Son, your ego is writing checks your body can't cash. Once again, we think we know a lot. Been around the block a few times, been chasing for 25 or 30 years. I found in doing what I do that the minute that my ego starts to get up there, I get humbled. And comes along a storm that just, you eat a whole bunch of humble pie. Just remember, too, that, every one of us needs to use common sense, and your number one priority, once again, should be getting home at the end of the day. Great quote from Tim Marshall. Sometimes there are days when it's just too risky. We've learned that on several days. His quote in my book, there are certain situations you simply have to abort, back out, and live to chase another day. Sometimes it's just, you just got to make that call. It might be a tough call, but it's a wise decision. All right, I want to put a little different spin on this tonight. A little psychology here. I've got a problem. I'm addicted to live auctions. I don't know what it is, but eBay and golden auctions, heritage auctions. See, I like to collect old sports cards. That one there is, I would love to have that card. That's a 1948 Leaf Jackie Robinson card. It says rookie year. It is worth a pretty penny. So I plan out these things days in advance. Maybe 3 days in advance, I know that the auction on that Jackie card's going to be ending. I got a plan in place in my mind. I'm only going to spend X amount of dollars. I'm not going to go over it. Then I get in that auction, and I start bidding. And then the heart starts pumping, and the adrenaline is going, and the time is ticking down. And I want that card really, really bad. Next thing you know, that limit that I had set for myself, that is gone. I've gone past that. And I keep on bidding until the very end. And let's say I win. Let's say I win it. It's happened. It's happened a couple times. But you know what usually happens about 30 seconds after that? What the heck did I just do? It's buyer's remorse. I could have bought that card like in a straight up regular priced auction, for $300 less than I just paid or more. And I think there's a similarity here. I think this goes on sometimes when we're out chasing. Psychologists study what they call auction fever. Many auction goers, me one of them, have described having intense emotions that cause them to overbid their preset limits. Psychologists call it pseudo-endowment. You feel an emotional attachment with that item, fueling your desire to own it, thus increasing your motivation to win it at all costs. I think that sometimes happens when we're out storm chasing. Maybe you've been out for 6 weeks now and you've come up empty every single time. And you finally get out in a storm and you see an opportunity. But it's a little bit of a risky chase day. Maybe you're out in East Texas. Maybe you're out in the woods. You don't have any line of sight on that horizon. Maybe these are quickly becoming wrapped in rain. Maybe you're on the wrong side of the storm and you're thinking about punching the core. It's when you let your emotions get the best of you and that common sense goes out the window. Maybe it's back on exit 51. And then you're making decisions with your emotions. That, my friends, is when you get in trouble. That is when you can make some bad decisions and get yourself in trouble. Don't do that. All right. I wanted to talk just a little bit about this. I know a lot of you chase because you love it. It's your passion. You know how important it is. Some of you do it for a living. Some of you get paid, for your time. I personally think you should. Absolutely. I know what you go through. I know the gas you burn through. I know the tires you blow out. I know the transmissions you drop. I know the engines that you burn, the windshields that are broken, the expensive equipment that you need to carry along. So dang it, why is it that TV station doesn't want to pay me for my stuff? Well, being on that side of things, let me say again, I fully support paying you. I wish we could have our chasers on the payroll. But unfortunately, there is a lot of video out there. And if a TV station can get it through other sources for free, that's what they're going to do. Shrinking budgets. I don't know if you know how expensive it is, but just my data feed alone for the TV station, I don't pay for it, thankfully, is $348,000 a year. That is just the data. That's not the cameras, the lights, salaries, all the expensive equipment that is just the fee for the data that we get in our TV station for weather alone on a yearly basis. shrinking budgets. Also, TV ratings aren't what they used to be 10, 15, 20 years ago. And so when it used to be that we could pay chasers, we can't anymore. Potential liability, too. News management's worried about that. If I pay this person for their video, does that mean that now they're our chaser? What happens if they get hurt out there? And boy, once you start getting, the attorneys involved and the lawyers and giving them, then that tends to scare them off as well. But I did ask some of my news producers, and, I said, when is a situation where you would really think about paying for video? They said, a couple exceptions for sure. Is it a big event? Is it a big event that's going to be a news story for multiple days that we can roll that video for our morning show, the noon show, the evening shows, the very next day? Now we're getting a lot of mileage out of this, and it becomes worth it for us to pay for it. Or an exclusive get. Maybe we can get something that our competition doesn't have. So that's another opportunity there. But I will tell you guys this. Even if you're airing your video on a television station with just a courtesy, that puts your name and your product in front of a lot of eyeballs, and that potentially can open some other avenues for making revenue as well. And of course, too, I would also remind you that it means a lot to what we do, the bottom line, and that is getting the message out. Those ground truth reports, that live video stream, even those short clips, it really does amplify our message on the air. I want to talk just a little bit about my book here, Menacing Skies. Released it a few years ago. It's got a lot in it. Tornado Genesis. Dr. Paul Markowski from Penn State University. Talked to him in depth about this. I go into that. There's weather history in there. D-Day, I don't know how many of you are familiar with the forecast that was made for D-Day. It was delayed 24 hours because 3 teams of meteorologists had the courage to tell General Eisenhower and the other generals that it wasn't a good idea to invade. They should delay it 24 hours. The coast of Normandy, the English Channel, is a notoriously stormy place on the planet. And the thing was, they only had a limited window because there was another storm coming behind the first one that was impacting Normandy. But there were 2 teams of British meteorologists, 1 team of American meteorologists, and their combined forecast. And think about that. No satellite, no radar, no computer models, pretty primitive. And yet they were able to put together a very accurate forecast with the help of cracking the German Enigma code. Cracking that code enabled them to intercept a lot of very, very important weather data that the Germans were keeping that helped them make that forecast as well. Talk about Delta Flight 191, the wind shear accident at DFW Airport. There are some incredible survivor stories in that book. Interview some of the leading experts in the country, including Dr. Markowski, Tim Marshall, John Nielsen Gammon, the Texas State climatologist, Dr. Josh Werman, Tim Samaras. I had the privilege of interviewing Tim a couple of times before his passing. Tom Bradshaw, the MIC at Fort Worth. A couple of my favorite quotes in the book from Pecos Hank. Maps and GPS can't predict flooded roads, and a stalled 100-coach train may be blocking your retreat when a bridge is out, when fallen trees are blocking your path, or a random deep pothole is anxious to tear your wheel right off its axle. Ain't that the truth? And Tim, sometimes storms will grow much larger, turn in a different direction, or accelerate. This one did all of that. And I think you probably know the storm I'm talking about, El Reno, Oklahoma.